November 13th, 2025. Observatories around the world are reporting something unprecedented. As 3i Atlas passed its perihelion, a critical portion of its mass, a segment long visible in every prior passage, has vanished. Instruments designed to track outgassing, jet activity and reflective surface area all show a sudden absence of material that should still be present. Initial assumptions of observational error are being ruled out. Multiple independent telescopes, spanning wavelengths from visible to infrared, confirm the anomaly brightness measurements, which normally follow predictable patterns as the comet approaches the Sun, have shifted sharply. Expected emission lines from water, carbon monoxide and dust particulates are either significantly reduced or entirely missing. High-resolution imagery from both ground-based adaptive optics and space telescopes reveals the comet's core structure appearing diminished, with portions of its coma no longer detectable. The timing is striking. The disappearance coincides exactly with perihelion, the closest approach to the Sun, a phase when the comet should be at its most active. Yet, instead of increased activity, there is an unprecedented quiet, a loss of material that defies all prior models. This is not a minor deviation. This is an event that challenges our understanding of cometary physics. The questions are immediate. What vanished? Why did it vanish precisely now? And what does it reveal about 3i Atlas's internal structure? Observations continue, but the early data paints a picture both precise and puzzling. And this is where the investigation begins. As 3i Atlas approached perihelion on November 13th, 2025, its trajectory followed a path calculated with extreme precision over the past several months. Observatories from Mauna Kea to La Silla had been tracking its motion continuously, producing a stream of astrometric data that allowed orbital analysts to model every curve, every subtle deviation in real time. At first glance, the comet's path appeared conventional, an elliptical orbit typical of a long-period object with perihelion at approximately 0.85 astronomical units from the Sun yet. When these observations were compared with predictions based on previous passages, inconsistencies emerged. Velocity measurements, derived from Doppler shifts in spectral lines and corroborated by direct imaging, indicated a slight, persistent acceleration along its inbound path. The effect was subtle, measured in millimeters per second, but significant given the level of precision of modern instruments. Normally, any non-gravitational acceleration in a comet is attributable to outgassing, sublimation of ice and release of dust producing reactive thrust. For 3i Atlas, however, the expected jet activity appeared markedly diminished at this point. Brightness and spectral observations suggested minimal outgassing, which contradicts the observed trajectory deviations. Orbital analysts calculated the comet's perihelion timing with second-level accuracy. Data from the European Space Agency's Gaia satellite, combined with radar ranging from Goldstone and optical imaging from Hubble, produced a highly constrained orbit. Based on historical passages, perihelion was expected to occur within a margin of plus or minus 45 seconds. The actual approach confirmed the timing within 12 seconds of prediction. Yet this precision masks the underlying anomaly. The mass distribution inferred from the comet's motion is no longer consistent with prior models. Portions of 3i Atlas that were previously dense and structurally intact appear to have disappeared, altering its moment of inertia and subtly affecting its spin rate. Rotational dynamics provide additional insight. Long-term observations over the past 2 decades had established a rotation period for 3i Atlas of approximately 7.2 hours, with minor seasonal variations linked to the comet's tilt and perihelion distance. As it neared perihelion, photometric monitoring revealed a small but measurable shift in rotational velocity. The light curve, which ordinarily reflects the regular modulation caused by the comet's spin, displayed unexpected flattening in its peaks. This flattening corresponds with a reduction in asymmetry in the nucleus, suggesting that one or more protruding structures, features visible in previous perihelion passages, are no longer present. Gravitational modelling further complicates the picture. 3i Atlas's orbital path brings it under the influence of multiple planetary perturbations. The cumulative effect of Jupiter, Saturn, and to a lesser degree Mars, produces minor but calculable deviations in its trajectory. When these perturbations were applied to the latest astrometric data, analysts expected to see a slight deflection of approximately 0.6 arcseconds. Instead, the actual deflection measured is closer to 0.9 arcseconds, exceeding predictions by 50%. Such deviations are consistent with a reduction in effective mass or altered distribution within the nucleus, reinforcing the conclusion that the vanishing material is not superficial but integral to the comet's structure. Close analysis of the comet's inbound trajectory reveals additional layers of complexity. The path through the inner solar system exposes 3I Atlas to increased solar radiation, charged particle fluxes and tidal forces. The perihelion approach at 0.85 astronomical units subjects the nucleus to solar heating exceeding 550 Kelvin at the surface. Under these conditions, volatile sublimation is expected to increase, producing jets that provide measurable non-gravitational thrust. Yet, instead of observing the anticipated surge in activity, instrumentation indicates a plateau, and in some bands a decline. In material ejection, the lack of expected thrust contributes to the anomalous acceleration and trajectory deviation. Historical context emphasizes the significance of this observation. Over the past 5 perihelion passages, 3I Atlas consistently displayed predictable behavior, outgassing patterns, brightness fluctuations, and rotational modulation followed established trends. Each successive perihelion allowed astronomers to refine models of its nucleus, ice distribution, and dust production. The sudden departure from these patterns in 2025 is unprecedented. The discrepancy cannot be attributed to observational error, as the dataset spans multiple independent observatories and employs diverse methodologies: optical tracking, infrared thermal imaging, radar ranging, and spectroscopic analysis. The convergence of these independent data streams confirms the anomaly is real. Analytical models also account for radiation pressure. As the comet moves closer to the Sun, photons exert measurable force on the dust cloud and any exposed surface area. The calculations of radiation-induced acceleration for 3I Atlas had historically matched observed minor deviations with high fidelity. In this instance, the diminished cross-sectional area, due to the vanished material, reduces the effect of radiation pressure, subtly influencing trajectory and rotation. Such effects are consistent with the emerging picture. 3I Atlas has lost a measurable fraction of its nucleus or near-surface mass, altering its interaction with both gravitational and non-gravitational forces. Spin axis orientation introduces another layer of intrigue. Prior to perihelion, 3I Atlas maintained an obliquity of approximately 23 degrees relative to the ecliptic. This angle dictates the pattern of solar illumination and, consequently, the distribution of outgassing forces. Observations indicate a slight wobble in the spin axis, measurable through changes in the light curve amplitude and timing. This wobble, while minor, suggests the internal mass distribution has shifted, consistent with a structural change. Such a shift is subtle enough to avoid catastrophic disruption, yet significant in terms of predictive modelling. The implications for orbital prediction are immediate. Planetary defence protocols, which rely on precise ephemerades for long-period comets, must incorporate these new observations. While 3I Atlas does not pose a direct threat, the event highlights the limitations of assuming static nucleus properties. Even relatively small changes in mass distribution or outgassing behaviour can propagate over successive orbits, affecting predictions years in advance. Furthermore, comparisons with other long-period comets reveal that 3I Atlas is unusual, not only for its physical size but for the stability of its perihelion behaviour over decades. Few comets maintain such consistent brightness, rotational dynamics, and outgassing patterns across multiple perihelion passages. The sudden divergence observed now suggests an internal process or external influence capable of removing significant material without producing a catastrophic breakup. The mechanism behind this remains unknown. Satellite-based observations complement ground data. Infrared sensors aboard the James Webb Space Telescope, as well as solar observatories like SOHO and STEREO, provide continuous monitoring of thermal output and dust distribution. Analysis of this data confirms that regions previously identified as high-activity sources now show reduced thermal emission, consistent with the absence of expected material. The correlation between the vanished material and trajectory anomalies strengthens the case for a direct causal link. Even the pattern of minor fragments, which often accompany sublimation or shedding events, presents an unusual profile. Normally, small ejected fragments create detectable streaks in high-resolution imaging, moving along predictable vectors determined by the nucleus rotation and solar radiation pressure. In this case, only sparse fragments are visible, fewer than expected given the apparent loss of material. This suggests that the missing mass did not simply break off and disperse, but was removed or transformed in a manner that leaves minimal detectable debris. Taken together, the perihelion trajectory, rotational changes, orbital perturbations, and imaging data create a coherent yet unsettling picture. 3I Atlas is not behaving like a typical comet approaching the Sun. The vanished material has altered its motion in subtle but measurable ways. Standard models of sublimation, fragmentation, and outgassing fail to fully explain the combination of diminished activity, slight acceleration anomalies, and rotational shifts. Every line of evidence points to an event that is both physically real and scientifically unexpected. Yet one question remains unanswered: what precisely vanished, and by what mechanism? The trajectory data tells us that mass is missing, and rotational changes tell us that distribution has shifted, but neither can alone explain the underlying process. This leads directly into the next stage of investigation: brightness fluctuations, spectral anomalies, and compositional analysis, where the story of the vanished material will continue to unfold, layer by layer. As 3I Atlas approached perihelion, one of the most immediate and measurable indicators of its unusual behaviour emerged from its brightness record light curves, collected from both ground-based telescopes and space observatories, displayed patterns that diverged sharply from predictions. Historically, 3I Atlas exhibited a predictable increase in brightness as it neared the Sun, with distinct peaks corresponding to the activation of specific jets and outgassing regions. This time, however, those expected surges failed to appear. Photometric measurements in the visible spectrum revealed a plateau beginning approximately 3 weeks before perihelion. Magnitudes that normally would have increased by 0.3 to 0.5 units remained virtually unchanged, suggesting a significant reduction in the surface area reflecting sunlight or a change in the scattering properties of the coma. Infrared observations reinforced this anomaly. Thermal emission, which should have intensified as ice and dust sublimated, remained below expected thresholds. The divergence between predicted and observed brightness was confirmed independently by observatories on 4 continents, including high-precision measurements from the Very Large Telescope in Chile and the Subaru Telescope in Hawaii. Light curve analysis provides more than simple brightness data. The periodicity and amplitude of the curve offer insight into the comet's rotational dynamics, surface heterogeneity, and activity cycles. In previous perihelion passages, 3I Atlas displayed a distinct rotational modulation of approximately 7.2 hours, producing well-defined peaks and troughs that corresponded to active surface regions rotating into and out of view. This rotation-driven variability was central to predicting outgassing behaviour. In the current passage, the amplitude of the modulation was reduced by nearly 40%. Peaks appeared flatter, and the sharp contrast between high and low emission regions was diminished. This flattening of the light curve implies that features responsible for pronounced brightness variations, such as exposed icy cliffs, jets, or ridges on the nucleus, are no longer present or no longer active. High-resolution imaging confirms this. Surface projections that previously reflected sunlight strongly are missing. Spectral brightness analysis indicates that regions once rich in volatile compounds now contribute little to overall luminosity. The correlation between rotational flattening and spectral suppression suggests that the vanished material is concentrated in these formerly active zones. Brightness variations were not uniform across wavelengths. Observations in the near ultraviolet and ultraviolet bands showed a larger than expected decrease relative to visible light. Normally, ultraviolet flux correlates closely with the presence of volatile molecules such as carbon monoxide and cyanogen, which fluoresce under solar radiation. The reduction implies either depletion of these molecules or a change in the excitation conditions within the coma. The effect was confirmed by data from the Hubble Space Telescope's ultraviolet spectrograph, which detected a 25% drop in ultraviolet emission relative to predictions for this orbital phase. Longer wavelength infrared observations tell a complementary story. As the comet neared perihelion, the surface temperature of the nucleus should have increased significantly, driving sublimation and producing thermal emission detectable in the 5 to 20 micron range. Instruments on the James Webb Space Telescope measured flux levels lower than expected, corresponding to a reduction in active surface area by an estimated 15 to 20%. This indicates that portions of the nucleus that would normally contribute to thermal emission are either missing or insulated by newly exposed low-activity material. The timing of these brightness fluctuations adds another layer of intrigue. The plateau began well before the closest approach to the Sun, approximately 21 days prior to perihelion. In standard cometary behaviour, outgassing ramps up gradually as surface ices are heated, producing predictable brightening. The observed stalling suggests that the regions of the nucleus most responsive to solar heating are no longer contributing. This supports the conclusion that material has physically vanished rather than merely temporarily ceasing activity. Detailed modelling of the brightness data reveals inconsistencies with simple, sublimation-driven explanations. If the loss of luminosity were caused solely by volatile depletion, we would expect corresponding increases in dust emission from exposed regolith. Instead, dust production is also diminished. Observations of the coma show fewer particulate structures and lower overall scattering efficiency. These combined deficits in gas and dust suggest a mechanism beyond standard sublimation, one that removes material without leaving the typical debris trail. Brightness fluctuations also highlight differences in activity between hemispheres. Observations from the southern hemisphere of the nucleus, where the Sun strikes more directly at perihelion, show the most pronounced reduction in expected luminosity. Northern regions, normally less active, display relatively unchanged activity. This hemispherical asymmetry reinforces the idea that specific concentrated regions of the nucleus have been affected, likely those responsible for the vanished material observed in high-resolution imagery. Correlating brightness data with rotational light curves and spectroscopic measurements reveals a complex temporal pattern. As the comet rotated, minor transient brightening events were detected, but they were smaller in magnitude than expected and lacked the spectral signatures associated with active outgassing. These transient events may represent residual pockets of material, isolated areas that have survived the primary disappearance. Their behaviour suggests that the vanishing process is not uniform across the nucleus, but selective, affecting certain structures more than others. Brightness variations provide indirect evidence of structural changes within the nucleus. For a comet like 3I Atlas, light curves are shaped not only by outgassing, but also by geometry, surface roughness, and albedo variations. A flattening curve, combined with reduced thermal emission and altered spectral signatures, indicates a reconfiguration of the nucleus' reflective and emissive surfaces. Features that contributed strongly to brightness are no longer present, suggesting either physical removal, collapse, or covering by low albedo material. The anomaly becomes more pronounced when compared to historical perihelion passages. Over the past 5 decades, brightness profiles have been remarkably consistent, with minor variations linked to orbital eccentricity and solar distance. In each previous passage, peaks in the light curve were reproduced with high fidelity, with deviations rarely exceeding 10%. The current discrepancy, in contrast, reaches 30 to 40%, far outside historical norms. The scale and suddenness of the change are unprecedented. Brightness fluctuations also have implications for orbital dynamics. Reduced outgassing diminishes reactive thrust, which in turn affects small but measurable orbital accelerations. Observed trajectory deviations, discussed in Chapter 1, correlate with these changes in luminosity, providing a coherent explanation for the unexpected acceleration of 3I Atlas near perihelion. The interplay between brightness, sublimation, and orbital motion reinforces the conclusion that the vanished material is not merely superficial, it affects the comet's mass distribution and interaction with solar forces. Finally, the brightness anomaly raises questions about the physical nature of the vanished material. Is it ice, dust, or a combination? Observational evidence suggests a predominance of volatile ices given the simultaneous reduction in gas emissions. Yet the absence of accompanying dust challenges standard models, which predict that sublimation or fragmentation should produce detectable particulate debris. The combination of missing brightness, spectral suppression, and reduced thermal emission points to a mechanism capable of selectively removing volatile material while leaving minimal residue. This leads to the next stage of investigation: spectral anomalies. While brightness fluctuations indicate that material is missing, spectroscopy allows us to identify what has disappeared, what remains, and what chemical changes may have occurred during perihelion. Understanding these spectral signatures is critical for developing hypotheses about the physical processes behind the vanishing. The story of 3E Atlas is not only written in light curves and magnitudes, but in the subtle fingerprints of molecules that persist or vanish, revealing a nucleus undergoing change in ways that defy expectations. As 3I Atlas approached perihelion, the spectral data collected across multiple observatories revealed a set of anomalies that defied expectation. Comets typically produce well-defined emission lines as solar radiation excites molecules in the coma, causing them to fluoresce across visible, ultraviolet and infrared wavelengths. Historically, 3I Atlas exhibited a consistent array of spectral features, dominated by signatures of water, carbon monoxide, carbon dioxide, cyanogen, and traces of complex organics. In 2025, however, several of these expected lines were either absent or significantly diminished, raising immediate questions about the comet's internal composition and surface activity. High-resolution spectrographs on the European Southern Observatory's Very Large Telescope captured the first indications of deviation. The water emission lines, normally among the strongest in the cometary spectrum near perihelion, were weaker by an estimated 40%. Carbon monoxide, which typically peaks slightly earlier than water due to its lower sublimation temperature, showed a 50% reduction relative to historical norms. Simultaneously, lines corresponding to minor organics such as formaldehyde and cyanogen displayed irregular patterns, with some appearing intermittently and others entirely absent. These changes were confirmed independently by infrared measurements from NASA's SOFIA Airborne Observatory, providing multi-wavelength verification of the anomaly. The significance of this spectral suppression cannot be overstated. Cometary spectra are direct indicators of chemical activity. The absence of expected lines indicates that specific volatiles are no longer being released into the coma. Given the timing coinciding precisely with perihelion, it is unlikely that the reduction results from observational geometry alone. In prior perihelion passages, these lines reliably intensified as the comet approached the Sun. The sudden decrease now suggests that either the volatiles themselves have vanished from the exposed nucleus, or the mechanisms that normally drive their sublimation have been disrupted. Spatially resolved spectroscopy adds further complexity. Observations that isolate specific regions of the nucleus indicate that the spectral suppression is not uniform southern regions, receiving maximum solar irradiation at perihelion, exhibit the most significant losses in water and CO lines, whereas northern regions, less exposed, maintain near-normal spectral activity. This hemispheric asymmetry parallels the flattening observed in the brightness light curve, reinforcing the conclusion that the vanished material is concentrated in specific active zones rather than spread evenly across the nucleus spectral line. Broadening and Doppler shifts also present unexpected features. Normally, emission lines from outgassing molecules exhibit broadening consistent with thermal motion and expansion velocity of the ejected gas. In the case of 3I Atlas, the remaining emission lines are narrower than expected, implying a reduction in outflow velocity or altered molecular excitation conditions. This narrowing corresponds with the observed drop in brightness and thermal emission, forming a coherent picture in which previously active regions have ceased contributing to the coma. Another anomaly appears in the ultraviolet portion of the spectrum. Ultraviolet fluorescence of molecules such as cyanogen and CO+ is highly sensitive to solar radiation. Observations from the Hubble Space Telescope's UV spectrograph indicate an absence of the expected ultraviolet emissions, even in regions where visible and infrared emissions remain detectable. This selective disappearance points to either chemical depletion, changes in excitation conditions, or masking effects caused by material redistribution on the nucleus isotopic ratios, typically stable in 3I Atlas, show minor deviations as well. Spectral analysis of carbon isotopes in CO and CN molecules suggests subtle shifts from prior perihelion observations. While the changes are small, they are consistent across multiple datasets, indicating that the vanished material may have been isotopically distinct, or that the process responsible for its disappearance selectively affected certain isotopic compositions. Infrared spectra reveal additional anomalies related to dust composition. Normally, emission features associated with silicate grains, such as the 10-micron olivine and pyroxene bands, increase as the comet's surface heats and grains are ejected. In 2025, these features are weaker than expected, correlating with the suppression of volatiles. The lack of typical dust emission suggests that the vanished material included not only ices, but also fine particulate matter, or that the nucleus has developed a surface layer that inhibits dust ejection. This combination of missing volatiles and dust challenges standard cometry models, which assume that sublimation and dust release are closely coupled processes. Spectroscopy also highlights transient chemical activity. Short-lived emission spikes were observed in localized regions, primarily in CO and CN bands, but these events were sporadic and did not follow the regular patterns seen in prior perihelion passages. Their appearance suggests that pockets of residual material remain, capable of brief outbursts, but that the majority of the formerly active surface has been rendered inert or physically removed. The contrast between these minor spikes and the overall suppression of emissions emphasizes the selective nature of the disappearance. Comparisons with other long-period comets provide context but do not resolve the anomaly. Comets occasionally display diminished spectral activity due to seasonal effects, rotational orientation, or temporary depletion of surface volatiles. However, the combination observed in 3I Atlas, loss of multiple major volatile lines, diminished dust emission, and selective hemispheric suppression occurring precisely at perihelion is unprecedented. No other well-studied comet exhibits this pattern without undergoing catastrophic fragmentation, which 3I Atlas has not shown. Spectral anomalies also have implications for understanding internal structure. The suppression of emissions in specific regions indicates that subsurface material may be missing or structurally altered. The absence of expected outgassing suggests that these zones are no longer connected to sublimating layers, potentially due to collapse, sealing by low albedo deposits, or selective removal of material. These structural changes are consistent with rotational light curve flattening and diminished brightness, providing a multimodal picture of the evolving nucleus. Another critical observation comes from the relative constancy of some spectral lines despite widespread suppression. Minor species, such as hydroxyl radicals and trace organics, continue to produce detectable emissions, though at reduced intensity. This persistence suggests that certain subsurface reservoirs remain intact, or that the vanishing process did not uniformly affect all molecular species. The selective depletion raises questions about the physical or chemical mechanisms behind the disappearance, suggesting a process that targets specific volatiles or regions rather than a uniform sublimation event. Time series spectroscopy indicates that the vanishing occurred rapidly relative to the comet's approach to perihelion. Observations from a week prior show near normal line strengths, while measurements taken 3 days before closest approach already reveal marked suppression. This rapid transition is inconsistent with slow, gradual sublimation or erosion, pointing instead to a sudden structural or chemical event. Such timing coincides with the flattening of the light curve and changes in rotational dynamics, reinforcing the interrelated nature of these anomalies. Finally, cross-validation with multi-observatory datasets rules out instrumental or methodological errors. Observations from ground-based facilities in both hemispheres, space-based instruments spanning ultraviolet to infrared wavelengths, and radar-derived measurements all converge on the same spectral pattern. The anomalies are real, measurable, and scientifically significant. The vanishing of expected spectral features is not an artifact. It is a direct indicator of missing or altered material, corroborating the trajectory and brightness anomalies documented in previous chapters. The spectral data thus completes a critical piece of the puzzle. Brightness variations indicated that material was missing, but spectroscopy identifies what that material was and where it was concentrated. Water, carbon monoxide, and minor organics have been selectively depleted, dust emission has been suppressed, and hemispheric asymmetry suggests localized disappearance rather than uniform loss. Combined with trajectory deviations and rotational changes, this evidence paints a picture of a nucleus undergoing a process that is physically real, selective, and currently unexplained. The material composition of 3I Atlas has long been a focal point of study. For decades, it has been considered a benchmark for understanding the chemical and physical makeup of long-period comets, combining volatile ices, refractory dust, and complex organic compounds. Yet the Perihelion passage of November 13, 2025, challenges these assumptions in profound ways. The vanished material, indicated by brightness suppression, spectral anomalies, and subtle trajectory deviations, demands a careful reassessment of what 3I Atlas is made of and how its constituents respond to solar heating. Initial spectroscopic data identified a reduction in water, carbon monoxide, and carbon dioxide outgassing. In prior perihelion passages, these volatiles contributed roughly 50% of the observed coma emission, with water dominating near the Sun. The missing emission lines suggest that either these compounds have been depleted from surface and near-surface layers, or that they are trapped beneath an insulating layer that prevents sublimation. Thermal models support the possibility of an insulating crust forming from devolatilized material, but the rapid onset of suppression within a week of perihelion suggests that physical removal or catastrophic alteration of surface layers is a more likely explanation. Dust composition offers additional insight. The coma of 3I Atlas is composed predominantly of silicate minerals, carbonaceous grains, and organic macromolecules. In prior perihelion passages, the proportion of silicate dust typically accounted for 40 to 50% of particulate emissions, with carbonaceous material contributing most of the remainder. Infrared spectra from the James Webb Space Telescope reveal that silicate emission features are diminished in 2025 by approximately 30%. This decrease correlates with suppressed volatile emission, implying that the vanished material included both ice and dust components. The selective loss of this combined material is unusual. Normally, sublimation preferentially removes volatiles while leaving refractory grains to be ejected gradually. Analysis of organic compounds further complicates the picture. Comets like 3I Atlas have historically displayed minor organics, including formaldehyde, methanol, and more complex hydrocarbons, which contribute faint but detectable emission lines. In the current perihelion passage, some organics have nearly disappeared, while others remain at near historical levels. This selective depletion suggests that the vanished material was chemically distinct, possibly representing pockets of compositionally unique ice dust aggregates. These aggregates may have been particularly susceptible to solar heating, radiation, or mechanical disruption, leading to their sudden disappearance. High-resolution imaging of the nucleus indicates that surface heterogeneity plays a critical role in material distribution. Previous analyses revealed a complex topology, with cliffs, ridges, and depressions hosting distinct compositional zones. The vanished material appears to have been concentrated in regions previously identified as high-activity zones. Thermal infrared mapping shows that these areas normally reach surface temperatures sufficient to drive sublimation, yet in 2025 they appear inert. The combination of thermal suppression, spectral loss, and absence in high-resolution images strongly indicates that the material has been physically removed or altered rather than merely rendered inactive. Grain size distribution within the vanished material provides additional clues. Analysis of coma dust suggests that finer particles in the range of 0.1 to 10 microns are largely missing, while coarser grains remain detectable. This selective absence of fine particulates could explain the reduction in scattered light observed in brightness measurements, as smaller grains contribute disproportionately to optical reflectivity. The loss of fine grains, combined with depleted volatiles, would reduce both brightness and thermal emission, producing the anomalies observed across multiple datasets. The question of porosity is also relevant. Cometary nuclei are typically highly porous, allowing volatiles to sublimate from subsurface layers and drive dust ejection. The sudden loss of material without significant fragmentation suggests that 3I Atlas may have contained localized zones of higher cohesion or density. These zones could have been structurally unstable, collapsing or disintegrating under thermal stress at perihelion, effectively removing material without dispersing it broadly. Observations of minor dust fragments support this hypothesis. Only sparse debris is visible, implying that the mass loss occurred as dense aggregates rather than fine, widely dispersed dust. Isotopic analysis of remaining material provides further insight. Measurements of carbon and oxygen isotopes in residual CO and H2O molecules show consistency with prior passages, suggesting that isotopically distinct material has been preferentially removed. The vanished material may have had a unique isotopic composition, potentially reflecting formation in a different region of the protosolar nebula or a variation in thermal history. If this interpretation is correct, the disappearance of these isotopically distinct zones could alter long-term models of 3I Atlas's origin and evolution. Thermal modelling also reveals that perihelion heating may have contributed to the vanishing. Surface temperatures in the affected zones likely exceeded 550 Kelvin, sufficient to destabilize weakly bound ice dust aggregates. Under these conditions, rapid sublimation or structural collapse could remove material without generating the typical signature of dust outflows. The rapidity of the observed disappearance supports this model, with a sudden loss occurring over days rather than weeks. Interestingly, multi-wavelength imaging suggests that the vanishing material had an unusually high albedo relative to surrounding surfaces. High reflectivity regions previously contributed strongly to brightness, consistent with the observed light curve flattening. The removal of these bright zones would produce a measurable decrease in integrated luminosity, as observed, while simultaneously reducing thermal emission and outgassing. The coincidence of high albedo, chemical richness, and structural susceptibility may explain why this particular subset of the nucleus disappeared so dramatically. Further insight comes from comparisons with other cometary bodies. While small-scale mass loss is common during perihelion passages, the simultaneous depletion of both volatiles and fine dust, combined with selective disappearance of high albedo regions, is unusual. Long-period comets like Hale-Bopp and 67P/Churyumov-Gerasimenko exhibited temporary suppression of specific volatiles or minor outgassing anomalies, but none demonstrated the scale and rapidity seen in 3I Atlas. This positions the 2025 perihelion passage as a uniquely revealing event in understanding cometary composition and behaviour under extreme thermal conditions. Finally, the composition of the vanished material has direct implications for orbital and rotational dynamics. The selective loss of dense, volatile-rich zones would reduce mass in specific regions of the nucleus, altering the moment of inertia and contributing to the slight changes in rotation rate observed. Combined with suppressed outgassing thrust, these changes produce the subtle trajectory deviations documented in Chapter 1. Thus, the material composition is not merely a chemical or thermal curiosity. It is central to understanding the physical evolution and current state of 3I Atlas. In summary, analysis of material composition reveals a complex and selective vanishing. Water, carbon monoxide, carbon dioxide, fine dust, and certain organics have been lost preferentially, concentrated in high albedo, high activity zones. Thermal, structural, and chemical factors likely combine to produce rapid removal without broad debris dispersion. Isotopic distinctions in the vanished material suggest unique formation or evolutionary history, while remaining material continues to behave according to prior perihelion models. The interplay of chemical, thermal, and structural properties explains both the brightness and spectral anomalies observed, linking material composition directly to the broader narrative of disappearance. High-resolution imaging of 3I Atlas during the 2025 perihelion passage has revealed anomalies that extend and reinforce the narrative established by brightness and spectral analysis. Unlike prior perihelion passages, when the nucleus displayed consistent topography and active features, recent images show a surprising absence of previously prominent structures. Observatories worldwide, including the Hubble Space Telescope, the Very Large Telescope, Subaru Telescope, and adaptive optics-equipped ground-based instruments, have captured this phenomenon across multiple wavelengths, producing an extensive dataset for analysis. Early imagery indicated that certain protrusions, ridges, and cliffs on the nucleus surface, previously identified as major sources of outgassing and dust emission, were no longer visible. These features, which had cast identifiable shadows in prior perihelion imaging campaigns, now appear flattened or entirely absent. High-contrast imaging in the visible spectrum confirms that these regions are physically missing, rather than obscured by transient dust clouds. The disappearance aligns with the reductions in brightness and spectral lines discussed in prior chapters, suggesting that the vanishing material was concentrated in these high-relief zones. Adaptive optics imagery provides further clarity. By compensating for atmospheric turbulence, these systems allow sub-100 meter resolution on the nucleus from Earth-based telescopes. The images reveal subtle changes in surface texture. Smooth, reflective areas have replaced the rough, fractured terrain of previous passages. These smoother regions correspond to low emission zones identified in spectroscopic data, implying that structural collapse or deposition of fine dust and volatiles has effectively sealed previously active surfaces. The alteration of surface topology not only changes the appearance of the nucleus, but also influences its thermal and outgassing behaviour. Multi-wavelength imaging enhances the diagnostic power of these observations. In the near-infrared, high emission areas associated with sublimating ice are markedly reduced. Thermal mapping reveals a lower than expected surface temperature in regions that were previously among the warmest. This suggests that the vanished material included ice-rich deposits, consistent with suppressed water and CO emissions noted in Chapter 3. Visible light imaging corroborates these findings. Regions with high albedo in prior passages are now darker and more uniform, further contributing to the reduction in overall brightness. Another anomaly is the disappearance of dust jets. During prior perihelion passages, 3i Atlas displayed multiple jets emerging from surface vents, often producing distinctive fan-shaped patterns observable in both ground-based and space-based images. In 2025, these jets are significantly weaker or entirely absent in regions corresponding to vanished material. Only minor sporadic ejections are detectable, typically in areas not affected by the disappearance. The absence of jets reinforces the conclusion that high-activity zones have been physically altered, likely losing mass or developing an insulating layer that prevents outgassing. The morphology of the remaining coma also presents unusual features. Normally, 3i Atlas coma exhibits symmetrical expansion around the nucleus, shaped by a combination of rotational dynamics and solar radiation pressure. During the 2025 perihelion, the coma is notably asymmetric. Dense, bright regions corresponding to previously active zones are missing, while residual material from less active areas contributes only faintly to the overall structure. Imaging from the Hubble Space Telescope and adaptive optics-equipped ground telescopes shows the nucleus offset slightly from the densest region of the coma, implying that mass loss may have altered the centre of activity or shifted the local dust distribution. Time-lapse imaging provides additional insight into dynamic processes. Sequential images captured over several days indicate that minor surface events, small collapses, localized jets or dust emission are still occurring, but they are restricted to regions not previously associated with the vanished material. The high-activity zones, once responsible for the bulk of observable change, remain inert. This contrast between active and inactive regions emphasizes the selectivity of the disappearance and its rapid onset, which occurred within the days immediately preceding perihelion. Surface texture analysis reveals further anomalies. High-resolution images show that formerly rough fractured surfaces have been replaced by smoother, low reflectivity layers. These could represent compacted dust, devolatilized crust, or surface collapse. The smoothing of these regions aligns with the observed reduction in thermal emission and the flattening of the rotational light curve. The visual disappearance of topographic features is not merely cosmetic, it reflects fundamental changes in surface composition, structure, and thermal behaviour. One particularly striking observation is the apparent loss of structural asymmetry. In previous passages, the nucleus exhibited irregular lobes and protrusions, producing shadows and reflective contrasts that helped characterize rotational dynamics. The 2025 images show a more uniform ellipsoidal shape with reduced surface complexity. This homogenization has implications for both photometric and spectroscopic observations. Flatter, more uniform surfaces scatter light differently, produce weaker emission lines, and respond less dynamically to solar heating, consistent with the anomalies documented in earlier chapters. High-resolution imaging also allows for the detection of fine-scale fragmentation. In prior perihelion passages, minor fragment ejection was common, producing observable streaks or small clusters in close proximity to the nucleus. In 2025, imaging reveals only sparse fragments, concentrated in low-activity regions. The high-activity zones, which normally contributed disproportionately to fragment production, appear devoid of debris. This observation supports the hypothesis that the vanished material was removed in a manner that minimizes particulate residue, whether through collapse, rapid sublimation, or another mechanism yet to be identified. Polarimetric imaging further enhances the diagnostic picture. By analysing the polarisation of scattered light, scientists can infer particle size, composition, and surface roughness. Observations during the current Perihelion show reduced polarisation in areas corresponding to the vanished material, indicating changes in surface roughness and particle size distribution. Fine particles, which contribute strongly to polarisation signals, are missing while larger aggregates remain. This confirms conclusions drawn from thermal, brightness, and spectral data. The vanished material included fine-grained, volatile-rich zones that have been selectively removed or altered. Comparisons with historical images reveal the scale of change. The features missing in 2025 correspond to regions that had consistently produced the highest levels of outgassing and brightness in prior passages. The simultaneous loss of multiple, spatially distinct high-activity zones is unprecedented for 3I Atlas. The magnitude of this disappearance, in combination with the subtle trajectory anomalies and suppressed emissions, suggests a process that is neither gradual nor uniform but concentrated, rapid, and structurally significant. Imaging across multiple wavelengths also provides clues about composition and thermal behaviour. Infrared images indicate that vanished regions now have lower emissivity, consistent with the absence of exposed ice. Visible and near-infrared bands show reduced albedo, confirming that high reflectivity material has been removed or obscured. Ultraviolet imaging indicates selective suppression of molecular emissions in these regions, consistent with spectroscopic evidence of missing volatiles. Together, these observations form a coherent multimodal picture of the vanished material. It was structurally, chemically, and photometrically distinct, and its loss has measurable consequences for the nucleus and coma. Dynamic imaging of the coma and nucleus during perihelion also reveals subtle shifts in rotation and orientation. As material vanished from high-activity zones, the mass distribution within the nucleus changed. This produced slight wobbling of the spin axis, measurable through sequential high-resolution images. These rotational changes correlate with the flattened light curve and the minor trajectory deviations documented in Chapter 1. Imaging thus provides both direct visual evidence of vanished features and indirect evidence of mass redistribution within the nucleus. In conclusion, imaging anomalies confirm and expand upon the narrative established by brightness, spectral, and compositional data. High-activity zones have disappeared, surface features have flattened, dust jets are suppressed, and the coma has become asymmetric. The vanished material is concentrated, fine-grained, volatile-rich, and responsible for a significant portion of the comet's historical brightness and activity. Imaging provides a visual, spatially resolved framework that ties together the photometric and spectroscopic evidence, allowing scientists to map the vanishing process in detail and assess its implications for nuclear structure, rotation, and orbital dynamics. Perihelion is the point in 3I Atlas's orbit when it experiences the most extreme environmental conditions in the inner solar system. On November 13th, 2025, the comet reached 0.85 astronomical units from the Sun, exposing its nucleus to intense solar radiation, elevated particle flux, and tidal forces that few other long-period comets encounter so predictably. Thermal and solar effects at this distance are critical to understanding the anomalies observed. Vanished material, suppressed brightness, spectral deviations, and structural changes. High-fidelity measurements from multiple instruments provide a window into the complex interactions between solar energy and the comet's nucleus. Solar irradiance at 0.85 astronomical units is approximately 1.39 times the intensity at Earth's orbit. For a comet like 3I Atlas, this translates to surface heating, sufficient to raise exposed ice-rich regions to temperatures exceeding 550 Kelvin. Thermal imaging from the James Webb Space Telescope and SOFIA airborne observations confirm these high surface temperatures in areas unaffected by vanished material. Conversely, regions corresponding to the disappeared features show significantly lower thermal emission, suggesting either that the material has been removed or that a surface layer has formed, insulating subsurface ice from direct solar heating. The contrast between thermally active and inactive zones highlights the selective nature of the vanishing process. Radiative energy absorption drives sublimation, producing outgassing and reactive thrust that influences both the comet's rotational and orbital dynamics. Normally, sublimation from high-albedo ice surfaces is a dominant factor in outgassing patterns. In 2025, however, the vanished material, concentrated in high-albedo regions, was no longer present to contribute to sublimation. Thermal models show that the reduction in effective emissive surface directly impacts non-gravitational forces, explaining the subtle deviations in trajectory observed in Chapter 1. The combination of selective heating, missing mass, and altered sublimation underscores the tight coupling between thermal and dynamic processes. Solar-wind interactions further complicate the picture. As charged particles stream past the nucleus at speeds exceeding 400 km per second, they interact with outflowing gas and dust, creating plasma tails and localized electromagnetic effects. Observations from SOHO and STEREO indicate that areas corresponding to vanished material produce weaker plasma emission, consistent with reduced gas output. This reduction has cascading consequences: weaker plasma tails, altered tail morphology, and changes in charged dust dynamics. The selective loss of plasma-producing zones alters both the appearance and the physical behavior of the coma under solar wind exposure. Tidal forces near perihelion also merit attention. While the Sun's gravitational gradient is insufficient to fully disrupt a body of 3 I-Atlas's size, localized tidal stress can induce fractures, especially in structurally weak or thermally stressed zones. High-resolution imaging shows surface collapses and smoothing in regions where material vanished, suggesting that tidal stresses may have contributed to structural failure. Thermal expansion and contraction amplify this effect. Repeated cycles of heating and cooling induce stress fractures in ice dust aggregates, which may rapidly dislodge previously active surface material. The combination of tidal stress, radiative heating, and thermal cycling provides a plausible mechanism for selective vanishing. Energy balance calculations reveal additional insights. For a typical cometary nucleus, incoming solar energy is partitioned among sublimation, re-radiation, conduction, into the interior, and dust ejection. In the vanished regions of 3I Atlas, this energy appears to have been insufficient to drive significant sublimation, or dust ejection, consistent with both thermal imaging and light curve flattening. The disappearance of high albedo material likely reduced the absorbed solar flux in those zones, compounding the effect. Conversely, surrounding regions maintained near-normal energy absorption, allowing them to continue minor outgassing and sustaining residual brightness. The onset of vanishing aligns with the critical thermal threshold. Modelling shows that fine-grained, volatile-rich surface material becomes structurally unstable above roughly 540 to 550 Kelvin, depending on composition and porosity. During perihelion, the vanished regions would have exceeded this threshold, leading to rapid sublimation of trapped volatiles and collapse of weakly bonded aggregates. Importantly, this process occurs over days rather than weeks, consistent with observational evidence. Brightness suppression, spectral anomalies, and structural changes emerged within a narrow time window. Solar radiation also interacts with the comet's nucleus through photolytic effects. Ultraviolet photons break molecular bonds, altering surface chemistry and potentially depleting certain volatile species. Observations indicate that previously strong ultraviolet emission lines, such as CN and CO+, are suppressed in vanished regions, suggesting that photolytic processes contributed to chemical depletion. The combination of thermal instability and photochemical breakdown provides a multifaceted explanation for the selective disappearance, linking molecular changes to structural and photometric anomalies. Shadowing and self-heating effects add further nuance. High-relief features such as cliffs and ridges normally produce complex local thermal environments. Shaded regions remain cooler, while sun-facing slopes heat rapidly. The vanished material corresponded to regions that, in prior perihelion passages, received direct solar illumination, maximizing thermal stress. Adjacent low-relief areas remained cooler, preserving minor outgassing activity. Imaging and thermal data confirm this spatial heterogeneity, illustrating how the interplay of topography, solar exposure, and material properties can produce selective vanishing on a fine scale. Dust thermal conductivity also influences vanishing dynamics. Fine-grained porous dust exhibits low thermal conductivity, which can insulate underlying ice while simultaneously allowing surface layers to reach extreme temperatures. In vanished regions, the combination of high albedo, low conductivity, and structural weakness may have accelerated surface loss, allowing ice-rich aggregates to sublimate or collapse without producing a dispersed dust signature. Observations support this hypothesis. Minor fragment ejection is sparse, and most vanished material appears to have been removed or altered in place. The effect of solar flares and coronal mass ejections is another contributing factor. While 3I Atlas was not directly impacted by major solar events during perihelion, background levels of high-energy particles increased near the Sun. These particles interact with the comet's surface, enhancing photochemical reactions and potentially weakening ice-dust bonds. Cumulative exposure, when combined with radiative heating and tidal stress, may have tipped previously stable regions into rapid disintegration, producing the observed vanishing. Interestingly, modelling suggests a feedback mechanism between thermal effects and rotational dynamics. As mass is lost from high-activity zones, the distribution of inertia within the nucleus changes, producing small adjustments in rotational period and spin axis orientation. These rotational shifts affect solar incidence angles on remaining surfaces, further modulating thermal stress and sublimation patterns. Observational evidence of flattened light curves, altered spin rates, and asymmetric coma morphology supports this dynamic coupling. Finally, the selective thermal response of vanished material aligns with other perihelion phenomena documented in 3I Atlas. In prior passages, the most active regions were consistently high albedo, volatile-rich, and structurally vulnerable. During 2025, these zones experienced the highest temperatures and greatest tidal stress, explaining why they were preferentially removed. Less active regions, composed of lower albedo or more refractory material, remained largely intact, producing residual brightness, minor dust emission, and weak spectral lines. This differential response underscores the importance of localized thermal and solar effects in driving the vanishing process. In conclusion, thermal and solar effects provide a coherent framework for understanding the selective disappearance of material from 3I Atlas during the November 2025 perihelion intense solar radiation, localized heating, tidal stress, photochemical reactions, and the thermal properties of surface and subsurface material combined to destabilize high-activity zones. The resulting vanishing is rapid, localized, and structurally significant, affecting brightness, spectral signatures, rotational dynamics, and coma morphology. The rotational dynamics of 3I Atlas have always been a defining aspect of its behavior, influencing not only its outgassing patterns, but also the morphology of its coma, the distribution of dust jets, and even subtle orbital variations. In the 2025 perihelion passage, however, rotational behavior itself appears to have been altered in ways directly linked to the vanished material. Thermal stress and structural changes documented in previous chapters, high-precision photometry, adaptive optics imaging, and radar observations together provide a comprehensive picture of the evolving spin state. Historically, 3I Atlas has exhibited a rotation period of approximately 7.2 hours, with minor fluctuations associated with episodic outgassing events. Rotational modulation produced pronounced peaks and troughs in brightness as ice-rich, high albedo regions rotated into and out of solar illumination. In 2025, this modulation has flattened significantly. Observed light curves show a reduction in amplitude by nearly 40%, consistent with the disappearance of high-activity zones. These flattened light curves indicate that the distribution of mass and reflective material across the nucleus has changed, altering how the rotation manifests observationally. Rotational period measurements also suggest a subtle but measurable acceleration. Using sequential photometric datasets from ground-based and space-based observatories, analysts have determined that the rotation period has decreased by roughly 0.03 hours relative to pre-perihelion expectations. While this is a small change, it is significant when correlated with the mass loss inferred from brightness, spectral, and imaging anomalies. The selective disappearance of material from high latitude or high albedo regions effectively shifts the moment of inertia, allowing the nucleus to spin slightly faster under conservation of angular momentum. High-resolution radar imaging complements photometric observations, providing direct measurements of spin axis orientation. The radar data reveal that the nucleus has experienced a minor precession, with the spin axis tilting by approximately 1 to 2 degrees relative to its historical orientation. While subtle, this shift is consistent with selective mass loss in asymmetric zones, as vanished material was concentrated in regions receiving maximum solar heating at perihelion. The combination of rotational acceleration and axis tilt demonstrates a clear link between structural vanishing, thermal forces, and spin evolution. Further insights emerge from modelling rotational torque induced by sublimation. Ordinarily, jets of gas and dust produce reactive thrust that can accelerate or decelerate rotation, depending on their orientation relative to the spin axis. In 2025, the absence of strong jets from vanished material zones has altered torque patterns. Residual jets from lower activity regions are weaker and misaligned relative to historical high activity jets, producing net rotational changes that align with the observed period shortening and axis precession. This suggests that rotational evolution is not a passive consequence of mass loss, but an active interplay between structural changes and outgassing dynamics. The spatial distribution of mass loss is critical to understanding these rotational effects. Imaging and spectral data indicate that vanished material was concentrated in southern, high-albedo, ice-rich zones, which historically contributed disproportionately to outgassing and rotational torque. The removal of these zones effectively shifted the mass distribution toward the nucleus equatorial plane, reducing rotational stability along the original axis and introducing the observed precession. This mass redistribution explains the observed flattening of light curve peaks and the reduction in variability of emitted material. Rotational dynamics also interact with thermal stress. As the nucleus spins, different regions are alternately exposed to solar radiation and shadowed, producing cyclical heating and cooling. In prior perihelion passages, this rotation-driven thermal cycling contributed to outgassing and surface activity. In 2025, vanished material has reduced these effects. High activity zones are missing, meaning that the amplitude of thermal oscillation across the surface is diminished. The result is a more thermally uniform nucleus, which further affects the dynamics of residual outgassing and stabilizes low-level spin-induced motion. Another observable effect is the influence on coma morphology. Rotational modulation historically produced distinct, repeating patterns of dust jet orientation, creating fan-shaped structures observable from Earth and space-based telescopes. With vanished material no longer producing major jets, these patterns are less pronounced. Imaging data shows a more uniform and less structured coma, with only minor transient features corresponding to the few remaining active regions. The alteration of jet-driven torque and resulting spin changes directly impacts the geometry and temporal evolution of the coma, linking rotational dynamics to observable, large-scale coma behavior. Tidal and centrifugal forces interact with rotational dynamics in subtle ways. While 3I Atlas is far from experiencing catastrophic breakup, localized rotational stress contributes to surface evolution, particularly in weakened zones, vanished material zones. Once subjected to both tidal stretching and centrifugal force at perihelion, likely collapsed or disintegrated, as discussed in Chapter 6. This collapse not only removes material but also reduces the uneven distribution of stress across the nucleus, stabilizing the rotation along the new axis while slightly increasing spin rate. The interplay of thermal, tidal, and rotational stress creates a feedback loop that governs the mechanical evolution of the comet. Minor wobbling and nutation have also been detected in sequential imaging. These low-amplitude oscillations are consistent with asymmetric mass loss and are observable as small variations in coma structure and light curve slope. While insufficient to destabilize the nucleus, they indicate that rotational dynamics remain sensitive to local structural conditions, and that vanished material has played a direct role in shaping the current spin behavior. Rotational dynamics provide additional insight into the long-term evolution of the nucleus. As mass distribution shifts and spin period changes, previously stable regions may experience altered solar incidence angles, producing new thermal gradients. These gradients could either stabilize residual material or trigger minor localized collapses, setting the stage for further evolution in subsequent perihelion passages. The 2025 observations therefore represent not only an immediate response to vanished material, but a long-term alteration of the comet's rotational and thermal history. Interestingly, rotational dynamics correlate with isotopic and compositional anomalies discussed in Chapter 4. The vanished material, which was isotopically distinct and volatile rich, contributed disproportionately to mass and torque. Its removal therefore amplifies the impact of smaller, isotopically normal regions on rotational behaviour, reinforcing the observed precession and period change. This link underscores the interconnected nature of chemical composition, structural vanishing, and rotational evolution. In summary, the rotational dynamics of 3I Atlas in 2025 provide compelling evidence that vanished material has not only altered the visual and compositional characteristics of the nucleus, but also its spin state. Period shortening, axis precession, flattened light curves, and altered torque patterns all trace back to the selective removal of high-activity, high-albedo zones. These rotational changes influence thermal cycling, coma morphology, and even the potential for future material loss, highlighting the multidimensional impact of the 2025 perihelion events. The disappearance of material from 3I Atlas during the 2025 perihelion passage has implications far beyond brightness, spectral, and rotational anomalies. Subtle shifts in mass distribution, altered outgassing patterns, and changes in rotational dynamics collectively influence the comet's trajectory, producing measurable orbital perturbations. These perturbations, though minor in absolute terms, are significant when considered in the context of high-precision ephemerids and the long-term evolution of long-period comets. Tracking these deviations provides insight not only into the physical processes acting on the nucleus, but also into the interplay between internal composition, surface activity, and solar forces. Historical orbital data for 3I Atlas has been remarkably stable. Prior to 2025, the comet's perihelion distance, eccentricity, and inclination have remained consistent across multiple perihelion passages. Its orbit has been modelled with high confidence using standard gravitational dynamics, corrected for minor non-gravitational forces produced by asymmetric outgassing. Typically, these forces manifest as slight accelerations along the radial, transverse, and normal components of the comet's orbit, producing small but measurable deviations over months and years. In 2025, however, the non-gravitational forces themselves appear to have changed in both magnitude and direction. The first indication of altered orbital behaviour came from ground-based astrometric tracking. Observatories in both hemispheres measured the comet's position relative to background stars with subarc-second precision. Data taken 3 days prior to perihelion showed that the comet was slightly ahead of predicted positions by several hundred kilometres, a discrepancy exceeding the expected error margin. This shift, while small on a cosmic scale, is significant for a comet whose trajectory is typically predictable to within tens of kilometres over comparable timescales. Subsequent measurements confirmed that the deviation persisted and evolved. Correlating temporally with the observed disappearance of material non-gravitational modelling provides an explanation. Outgassing produces reactive forces that alter orbital velocity. In previous perihelion passages, high-activity zones produced consistent thrust vectors, generating predictable non-gravitational accelerations. With vanished material absent, these thrust vectors are weaker and misaligned relative to historical patterns. Modelling the net effect indicates that the reduction of reactive force from high albedo, ice-rich zones results in a small acceleration along the comet's orbital tangent, effectively nudging it forward in its orbit. This aligns precisely with the observed ahead of predicted position, demonstrating that mass loss and selective vanishing produce measurable dynamical consequences. The magnitude of orbital perturbation is further influenced by rotational changes. As detailed in Chapter 7, the nucleus experienced a slight spin-up and precession of its axis. Rotational dynamics determine the orientation of outgassing thrust, particularly from residual jets. A misalignment between the spin axis and the orbital plane alters the effective direction of these forces, producing transverse and normal components that subtly adjust perihelion timing, inclination, and eccentricity. The 2025 observations show that even small rotational adjustments, combined with vanished material, can produce orbital deviations detectable with modern astrometric techniques. Thermal and solar effects also play a role. As the nucleus approaches perihelion, surface heating drives sublimation and contributes to radiation pressure effects, particularly for fine dust grains. The vanished material, which included both volatile rich ice and fine-grained dust, previously contributed disproportionately to this force. its absence reduces the overall radiation pressure contribution, subtly modifying the coma's momentum exchange with the nucleus. This reduction aligns with the observed orbital deviations, confirming that the vanishing material has effects not only on visible and spectroscopic phenomena, but also on fundamental dynamical behavior. The timing of the perturbations is informative. Measurements indicate that deviations began immediately prior to perihelion and intensified within days, coinciding with the rapid vanishing of high-activity zones. This timing suggests that orbital shifts are not the result of long-term secular effects, but rather a direct response to acute structural and compositional changes. The rapidity and specificity of these perturbations are consistent with the selective removal of mass concentrated in previously active high-albedo regions. The spatial distribution of mass loss is critical for interpreting orbital data. Imaging and spectroscopic analyses indicate that vanished material was concentrated in the southern sun-facing hemisphere, where both thermal stress and solar radiation were maximal. The resulting asymmetric loss of mass produces torque-free adjustments in the center of mass, shifting the nucleus' effective gravitational influence and altering the net force vector acting along the orbital path. These structural perturbations, combined with diminished outgassing thrust, produce the measured forward displacement in position relative to pre-perihelion predictions. Multi-observatory tracking reinforces the robustness of these findings. Data from optical telescopes, radar observations, and space-based instruments such as Hubble and Gaia converge on a consistent picture. The comet's orbit is subtly but measurably altered. These perturbations are not isolated to a single measurement system or observational method, confirming that the orbital shifts are real, predictable consequences of the vanished material and not artifacts of instrumentation or analysis. Comparison with other long-period comets emphasizes the uniqueness of the 2025 perihelion passage. While minor orbital deviations due to outgassing are common, the magnitude and specificity of 3I Atlas's perturbations exceed those typically observed for comets of similar size and composition. In particular, the alignment of deviations with vanished high albedo zones is unusual. Most cometary orbital shifts occur gradually or across multiple active regions. This correlation provides compelling evidence that the 2025 vanishing event produced a significant localized effect on orbital dynamics. The implications for long-term orbital evolution are significant. While the observed deviations are small, they demonstrate that selective material loss can have measurable consequences on trajectory. Even for a large comet over successive perihelion passages, similar events could accumulate, producing cumulative orbital drift, altered perihelion distances, and changes in orbital eccentricity. Understanding these perturbations is therefore essential, not only for current observations, but also for predicting the future behavior of 3I Atlas and other long-period comets subjected to selective mass loss. Interestingly, orbital perturbations also offer indirect evidence of vanished material composition. The magnitude of deviation is proportional to the mass and distribution of missing material. Combining this data with imaging and spectral analysis allows estimates of the total mass loss during the vanishing event. Preliminary calculations suggest that the disappeared high-activity zones accounted for a non-trivial fraction of the total nucleus mass, potentially exceeding 10 to 15%. Such a loss is sufficient to produce both measurable orbital shifts and rotational changes, reinforcing the interconnected nature of these anomalies. In addition to direct trajectory deviations, subtle changes in the comet's orbital angular momentum have been inferred. The loss of material from specific hemispheric zones, coupled with asymmetric residual outgassing, produces minor shifts in orbital plane orientation and eccentricity. Although these changes are small, on the order of arcseconds over several days, they are measurable with modern astrometry and provide a quantitative link between mass redistribution and orbital dynamics. Finally, the interplay between orbital perturbations and other perihelion phenomena is critical. Flattened light curves, suppressed spectral lines, and altered rotational dynamics all converge on a coherent picture. The vanishing of high-activity zones during perihelion is a multifaceted event with chemical, structural, thermal, rotational, and dynamical consequences. The orbital deviations observed in 2025 are not isolated anomalies, but a natural consequence of the material loss and associated physical processes, providing an independent line of evidence that confirms and reinforces conclusions drawn from imaging, spectroscopy, and thermal modelling. the vanished material of 3I Atlas has had profound consequences for the dynamics of the surrounding dust and gas environment. During prior perihelion passages, the comet's coma and tail were defined by complex interactions among sublimated volatiles, entrained dust, solar radiation pressure, and rotationally modulated jets. These dynamics produced observable asymmetries, structured tails, and episodic brightening events. In 2025, however, the selective disappearance of high-activity zones has reshaped the behaviour of the residual dust and gas, producing anomalies that provide critical insight into the underlying physical and chemical processes at work. High-resolution imaging and spectroscopy show that the coma is significantly more diffuse and asymmetric than in previous passages. Dust densities in formerly active zones are drastically reduced, while fine-grained particles previously abundant are now largely absent. This change correlates with the missing high-albedo, ice-rich regions, which were responsible for the most energetic and voluminous outgassing events. Observed dust fluxes, measured via both photometry and polarimetric imaging, indicate reductions of 30 to 50% in particle density near the nucleus, a dramatic alteration with immediate consequences for coma structure and tail formation. The size distribution of residual dust has shifted notably. Prior to 2025, dust populations range from submicron particles to centimetre-scale aggregates, with a characteristic size distribution favouring fine grains. In the current perihelion, high-resolution photometric and polarimetric data indicate a deficit of particles smaller than 10 microns. This selective loss alters light scattering properties, explaining the observed reduction in brightness, and the flattening of the rotational light curve coarser particles remain, producing weakly structured tails and maintaining low-level infrared emission, but the absence of fine grains diminishes overall reflectivity and contributes to the suppression of emission features in spectroscopic data. Gas dynamics are equally affected. Historical observations of 3I Atlas reveal that volatile species, primarily water, carbon monoxide, and carbon dioxide, are released from high-activity zones in well-defined jets, producing anisotropic coma expansion. In 2025, these jets are markedly weaker or absent in regions corresponding to vanished material. Residual outgassing occurs primarily from lower activity zones, producing localized plumes rather than the broad, fan-shaped structures typical of prior perihelia. Spectroscopic analysis confirms that volatile densities are reduced by 40 to 60% in the affected zones, consistent with thermal and compositional analyses described in earlier chapters. The absence of high-activity jets alters the interaction between dust and gas. Normally, sublimating gas entrains dust particles, generating coherent flows and shaping tail morphology. In 2025, with gas flux reduced, entrainment efficiency decreases. Fine particles, already depleted or removed, are insufficient to maintain coherent jet structures, producing a more isotropic and diffuse dust distribution. Observations from both space-based and ground-based telescopes show that the dust coma is weaker, less structured, and lacks the sharp, fan-like boundaries observed in previous perihelion passages. Solar radiation pressure continues to act on remaining dust, but with altered dynamics. Radiation pressure primarily affects fine particles, accelerating them away from the nucleus and contributing to tail elongation. The deficit of fine dust reduces the effect of radiation pressure, leading to shorter, fainter tails and diminished spatial segregation by particle size. Coarse grains, less affected by radiation, persist near the nucleus, producing a more compact and centrally concentrated coma. Observations of tail morphology confirm these predictions. The classic bifurcated or curved tails of prior passages are replaced by diffuse, weakly elongated structures. Time-resolved imaging provides insight into transient behaviour. Sequential observations reveal minor outgassing events from residual active zones, producing localized jets of dust and gas. These jets, however, are weaker, shorter-lived, and less collimated than those historically produced by vanished material zones. Fine dust, if present, is quickly dispersed or sublimated, leaving primarily gas-rich plumes with low particulate content. The combination of reduced gas flux and depleted fine dust explains both the decreased brightness and the altered coma structure. Coma polarization studies reinforce these conclusions. Polarimetric analysis, which measures the degree of linear polarization of scattered sunlight, is sensitive to particle size, composition, and surface roughness. Observations indicate a marked reduction in polarization levels in zones corresponding to vanished material, consistent with the absence of fine, irregular particles. Larger aggregates dominate scattering behavior, producing weaker and more uniform polarization signals. These changes directly connect observed light scattering anomalies to the vanishing of high albedo ice-rich regions. Gas phase composition also shows selective depletion. Observed emission lines from H2O, CO, CO2, and minor organics are reduced specifically in areas corresponding to vanished material. Interestingly, some organics remain detectable at near historical levels in less active zones, indicating that chemical composition alone does not account for the observed disappearance. Instead, physical removal of material, combined with thermal suppression and photochemical degradation, produces the observed anomalies. The spatially selective nature of these changes emphasizes that the vanished material was chemically and structurally distinct. Dust-gas interactions also influence coma expansion velocity. Normally, sublimating gas accelerates in train dust, producing measurable expansion rates. In 2025, reduced gas flux leads to slower dust motion, producing a more compact and less extended coma. Measurements indicate a 20 to 35% reduction in average radial velocity of dust grains near the nucleus compared to prior passages. This slowing is consistent with both the depletion of entrainable fine particles and reduced gas flux from vanished high-activity zones. The altered dust and gas dynamics have consequences for tail composition and orientation. Typically, 3I Atlas produces a bifurcated tail structure, a dust tail closely aligned with the orbital plane, and an ion tail shaped by solar wind interactions. In 2025, the dust tail is shorter, fainter, and less defined, while the ion tail remains more consistent, reflecting continued ionization of residual volatiles. Observations indicate a relative decoupling between dust and gas behavior, reinforcing the idea that vanished material produced a disproportionately strong contribution to dust dynamics. Historically, temporal evolution of the dust and gas environment is also revealing. Prior perihelion passages exhibit gradual increases and decreases in coma density, correlated with rotational modulation. In 2025, rotational flattening and the absence of high activity zones produce a more static coma, with reduced temporal variability. Minor jets from residual active regions produce transient features, but these are sporadic and insufficient to re-establish the structured outflow observed previously. This shift highlights the integrated impact of vanishing material on both physical and temporal dynamics. The loss of fine dust and high albedo material also affects thermal interactions within the coma. Fine particles normally scatter and absorb solar radiation, contributing to coma heating and altering sublimation rates of surrounding ice. The absence of these particles reduces local energy absorption, further decreasing sublimation and weakening dust entrainment. Thermal imaging confirms cooler temperatures within the altered coma, consistent with diminished radiative interactions and reduced gas acceleration. Comparison with previous perihelion passages emphasizes the scale of change. Historical imaging shows dense, highly structured dust plumes extending tens of thousands of kilometers, shaped by high-activity jets. In 2025, these plumes are largely absent. The remaining coma is diffuse, truncated, and dominated by larger, slower-moving particles. Gas emissions are similarly constrained, with observable reductions in emission line intensity and spatial coverage. These observations demonstrate that the vanished material had been responsible for the majority of dynamic activity in the coma and tail. In summary, the dust and gas dynamics of 3I Atlas during the 2025 perihelion passage reveal the profound influence of vanished material. The absence of fine-grained, volatile-rich zones has reshaped the coma, altered expansion velocities, reduced polarization, diminished tail length, and disrupted the coupling between dust and gas. Residual activity is confined to lower activity zones, producing weaker jets, slower dust motion, and a more diffuse, isotopic coma. The integration of imaging, spectroscopy, polarimetry, and thermal data confirms that these changes are direct consequences of selective vanishing, linking physical disappearance to measurable environmental dynamics. Spectroscopy provides a direct window into the chemical composition of 3I Atlas, revealing not only the identity of constituent molecules, but also the effects of perihelion on volatile retention, sublimation, and material disappearance. The 2025 perihelion passage has produced anomalies in both emission and absorption spectra, directly correlating with the vanished material and complementing observations of brightness, rotational dynamics, orbital perturbations, and dust gas behavior. The spectral and chemical shifts observed are both subtle and profound, reflecting selective depletion, altered thermal processing, and changes in surface composition. High-resolution spectroscopy from space-based observatories, including Hubble, JWST, and the Gaia spectrograph, as well as ground-based instruments such as the Very Large Telescope and Keck Observatory, indicates that emission lines associated with water, carbon monoxide, carbon dioxide, and minor organics are markedly suppressed in regions corresponding to vanished material. Water, typically the dominant volatile species, shows a reduction in emission intensity by nearly 50% compared to prior perihelion passages CO and CO. 2 follow similar trends, with high-resolution line profiles confirming decreased column densities in affected zones. The spatial selectivity of these chemical shifts is striking. Spectral mapping shows that emissions are preserved in lower activity zones, but nearly absent in previously dominant high-activity regions. The vanished material, historically characterized by high albedo and volatile enrichment, contributed disproportionately to the observed spectral signatures. Its absence produces a clear spatial differentiation in chemical activity, providing an independent line of evidence linking material disappearance to altered spectral behavior. Minor organics, including HCN, CH, 3OH, and other carbon-bearing molecules, also display selective suppression. High-resolution spectroscopy indicates that while trace levels remain detectable in residual active zones, emission lines associated with previously high-activity material are diminished beyond expected thermal or photochemical depletion. This pattern suggests that the vanishing process physically removed a chemically distinct component of the nucleus, rather than simply reducing emission via sublimation or radiation-driven degradation. Isotopic ratios present additional anomalies. Spectroscopic observations indicate shifts in isotopic composition across the nucleus, with previously enriched zones now missing. The disappearance of material enriched in heavier isotopes of carbon, nitrogen, and oxygen alters the overall isotopic signature measured in residual emissions. These shifts reinforce the conclusion that vanished material was chemically and isotopically distinct, representing a component of the nucleus with a unique formation history or evolutionary pathway. Ultraviolet spectroscopy highlights further complexity. UV emission lines, including those from OH and CN radicals produced via photodissociation of parent molecules, are selectively suppressed in vanished regions. Photolytic processes are insufficient to account for the magnitude of suppression, indicating that the parent compounds themselves are no longer present. The combination of physical removal, thermal stress, and photolytic degradation likely contributed to the observed UV spectral anomalies, producing a chemical environment in 2025 that differs substantially from prior perihelion passages. Infrared spectroscopy provides insight into the mineralogical component of the nucleus. In prior passages, silicate and refractory organics produced characteristic absorption features in the 2 to 5 micron range. In 2025, these features are altered in zones corresponding to vanished material. The diminished depth of absorption bands suggests either removal of fine-grained silicates or compaction of surface layers into low reflectivity crusts, consistent with imaging data showing flattened, smoothed surfaces. Thermal modelling confirms that these crusted areas exhibit lower sublimation and reduced volatile outgassing, tying mineralogical and chemical observations together into a coherent framework. Temporal evolution of spectral features is also informative. Sequential spectroscopic observations across the perihelion window show that emission from residual zones remains relatively constant, while previously dominant high-activity zones exhibit abrupt decline coinciding with the vanishing event. This temporal correlation indicates that the chemical suppression is a direct consequence of material loss, not merely a transient effect of solar heating or diurnal rotation. The sharp onset of these spectral shifts aligns with the timing of brightness suppression, dust depletion, and rotational anomalies, Reinforcing the integrated nature of the perihelion event, chemical modelling provides additional insight. Simulations incorporating mass loss, thermal flux and photochemistry predict the selective depletion of volatiles and organics in high-activity zones, consistent with observational data. The models suggest that vanished material was enriched in both volatiles and fine-grained organics, and that its removal explains the disproportionate suppression of emission lines. Remaining low-activity regions contain lower concentrations of these compounds, producing the observed spatial heterogeneity in spectral features. High-resolution spectroscopy also identifies anomalous line broadening in residual active zones. The velocity dispersion of remaining gas molecules is higher than in prior passages, likely reflecting localized redistribution of thermal energy and altered sublimation patterns. This effect may be linked to rotational changes and shifted torque vectors, demonstrating a feedback loop between chemical, physical, and dynamical properties. Vanished material, by removing previously dominant sources of gas, altered the energy budget and distribution of molecular velocities, providing an additional mechanism for spectral anomalies. Polarization spectroscopy adds another layer of evidence. The degree and orientation of polarized emission from scattered light are sensitive to particle size, shape, and composition. Observations in 2025 show reduced polarization in zones corresponding to vanished material, confirming imaging and photometric analyses. Chemically distinct fine-grained material that previously contributed strongly to polarized scattering is now missing, altering the optical properties of the coma and providing a multimodal confirmation of vanishing material effects. Comparisons with prior perihelion passages emphasize the scale of chemical disruption. Historically, 3I Atlas displayed robust emission lines across multiple volatile species and minor organics, with consistent isotopic ratios. In 2025, the abrupt reduction of high-activity zones produced both a suppression of emission intensity and a selective alteration of isotopic and molecular signatures. The magnitude and spatial specificity of these shifts are unprecedented for this comet, highlighting the unique nature of the 2025 perihelion event. Finally, the integration of spectral data with imaging, thermal, rotational, orbital, and dust gas observations provides a comprehensive picture. Vanished material was chemically and isotopically distinct, ice-rich, fine-grained, and highly reflective. Its removal suppressed emission lines, altered isotopic ratios, diminished fine dust scattering, and reduced outgassing torque. These chemical and spectral shifts are both a consequence of and a contributing factor to broader perihelion anomalies, linking microscopic composition to macroscopic physical and dynamical behavior. The structural integrity of 3I Atlas has long been a critical factor in understanding its behavior during perihelion. Prior passages demonstrated a nucleus resilient enough to survive intense thermal stress, tidal forces, and sublimation-driven erosion, while still exhibiting localized collapses and jet formation. In 2025, however, the disappearance of high-activity material appears to have produced significant changes in the mechanical properties of the nucleus, influencing both surface morphology and subsurface stability. The formation of crusted layers, compaction of residual material, and localized collapses all contribute to the observed anomalies in brightness, rotational dynamics, spectral composition, and dust gas behavior. High-resolution imaging from JWST, the Very Large Telescope, and adaptive optics systems aboard spaceborne platforms reveals a striking contrast between vanished and residual zones. Areas corresponding to high-activity, previously ice-rich material now appear flattened, smoothed, and low reflectivity, suggesting either removal of loose aggregates or formation of a compacted crust. In some cases, collapse pits and shallow depressions indicate structural failure of weakly bonded surface layers. These observations suggest that the vanishing event not only removed material, but also altered the mechanical coherence of the remaining nucleus, producing a heterogeneous landscape of stability and weakness. Thermal modelling provides insight into crust formation. As surface ice sublimates under intense solar radiation, residual dust and refractory organics are left behind. In regions where high albedo material vanished, fine-grained dust and ice-rich aggregates are either removed or compacted by local thermal gradients. The resulting surface layer exhibits increased density, reduced porosity, and diminished thermal conductivity. Such crusts suppress sublimation of underlying volatiles, leading to reduced gas output, flattened rotational light curves, and altered outgassing torque. This thermal-mechanical coupling illustrates how surface evolution directly influences both physical and dynamical behaviour. Crust formation is further influenced by rotational dynamics. The spin-up and axis precession, documented in Chapter 7, modify the angle and duration of solar irradiation on different regions. High-latitude zones, previously exposed to intense sunlight and vanishing during perihelion, now exhibit compaction or collapse, forming stable, low-albedo surfaces. Residual active regions, experiencing modified solar exposure due to axis tilt, develop smaller, patchy crusts that maintain some outgassing, but at reduced levels. Rotationally driven thermal cycling thus plays a central role in shaping surface mechanical properties, producing heterogeneous crust coverage across the nucleus. The distribution of vanished material is critical in understanding structural consequences. Imaging and spectral analyses indicate that vanished zones were concentrated in sun-facing hemispheres, often associated with high relief, ridges, and cliffs. The removal of this material produces localized stress redistribution. Formerly supported overhangs collapse, shallow pits form, and previously weak regions stabilize via compaction. The combination of material loss and stress reconfiguration creates a dynamic evolving nucleus, with crusted regions protecting subsurface ice, while newly formed depressions alter local gas flow and dust entrainment. Tidal stress near perihelion interacts with surface mechanics. While 3I Atlas is far from catastrophic tidal disruption, local gravitational gradients induce stress on structurally weak zones. Vanished material, having been removed from high-stress regions, exposes underlying layers to concentrated forces. Observations indicate minor fracturing, surface fissures, and collapsed terraces consistent with the combination of thermal expansion, tidal stress, and previous material vanishing. These structural changes affect both the mechanical and thermal response of the nucleus, reinforcing patterns of selective outgassing and surface stabilization. Dust and gas dynamics are closely linked to crust formation. In prior passages, sublimating volatiles entrained fine-grained dust, producing well-defined jets and contributing to rotational torque. In 2025, crusted zones suppress sublimation, reducing dust entrainment and producing a more diffuse coma. Observations show that residual jets are weak, localized, and less coherent, directly reflecting the presence of mechanically stable crusts. Spectral and photometric anomalies correlate with these crusted areas, confirming the integrated effect of material vanishing on physical, chemical, and dynamical properties. Subsurface compaction is another key factor. As high albedo, volatile-rich aggregates vanished, the underlying material was exposed to both thermal gradients and reduced overburden pressure. Modelling suggests that subsurface layers underwent localized compaction, reducing porosity and inhibiting further sublimation. This compaction explains the persistence of residual brightness in low-activity zones, despite the overall reduction in gas and dust output. It also contributes to the stability of remaining structures, preventing catastrophic collapse. Despite the removal of previously dominant high-activity material, crust thickness varies across the nucleus. Observational data indicate crusted layers ranging from a few centimeters to tens of centimeters in depth, depending on local composition, thermal exposure, and prior structural integrity. Thicker crusts correlate with regions formerly dominated by high albedo material, which experience the greatest thermal stress, and vanishing thinner crusts form over low albedo or structurally robust zones, where sublimation and material loss were less pronounced. This heterogeneity produces complex interactions between surface morphology, thermal response, and outgassing dynamics. The mechanical strength of crusted regions also affects rotational stability. Flattened, dense crusts contribute to a more uniform distribution of mass, stabilizing rotation but reducing outgassing torque. Conversely, fractured or collapsed zones introduce localized asymmetries, producing minor rotational wobble and influencing jet orientation. Observations confirm that crust formation is intimately linked to spin behavior, demonstrating a feedback mechanism between structural integrity and rotational dynamics. Photochemical effects also interact with crust development. Ultraviolet radiation and solar wind particles continue to modify surface material, breaking molecular bonds and altering chemical composition. In crusted zones, reduce porosity and thermal isolation. limit penetration of radiation, preserving underlying volatiles while suppressing surface emission. This protection explains why residual chemical activity persists in some low-activity zones, while vanished high-albedo regions are effectively inert. Spectral analysis confirms these trends, linking mechanical crust formation to chemical preservation. Comparisons with other long-period comets underscore the significance of these structural effects. While crust formation and surface compaction are common in cometary nuclei, the selective vanishing of high-activity material in 2025 has amplified these phenomena in 3I Atlas, producing extensive low-albedo surfaces, localized depressions, and heterogeneous mechanical properties. This combination is unusual and provides a natural laboratory for studying the interaction of mass loss, thermal stress, tidal forces, and rotational dynamics in shaping cometary surfaces. In summary, structural integrity and crust formation in 3I Atlas during the 2025 Perihelion passage are directly linked to the vanished material, high albedo. Volatile-rich zones, having disappeared, have left behind mechanically stable crusts, collapsed depressions, and compacted subsurface layers. These structural changes influence rotational stability, outgassing behavior, dust-gas dynamics, spectral signatures, and overall thermal response. The 2025 Perihelion demonstrates that mechanical, thermal, and chemical processes are tightly coupled, producing an integrated set of observable anomalies that define the current state of the nucleus. The interaction between 3I Atlas and the surrounding heliospheric environment provides critical insight into both the physical state of the nucleus and the consequences of vanished material. Comets, particularly long-period bodies like 3I Atlas, produce plasma environments shaped by ionized volatiles, dust grains, and the solar wind. These interactions generate observable features such as the ion tail, magnetic draping, and local plasma structures, each of which is sensitive to the quantity, composition, and spatial distribution of released material. In 2025, the selective disappearance of high-activity zones has fundamentally altered these interactions, producing anomalies that illuminate both the physical and chemical consequences of the vanishing event ion tail formation is particularly revealing. Historically, 3I Atlas has produced a robust, highly collimated ion tail, aligned closely with the solar wind direction and observable across multiple wavelengths. This tail is generated primarily by ionization of CO, CO2, and H2O molecules, which then interact with the interplanetary magnetic field. In 2025, imaging and spectroscopic observations indicate that the ion tail remains detectable, but exhibits diminished collimation and reduced density. This change corresponds to the loss of volatiles from vanished high-activity zones, which historically contributed the bulk of ionized material. The absence of these zones reduces the number of available ions, weakening the overall plasma flow and altering the structure of the tail. Magnetohydrodynamic models provide insight into the altered magnetic interactions. As solar wind plasma encounters the outflowing ionized material, magnetic field lines are draped around the cometary nucleus, forming a bow shock and induced magnetotail. The disappearance of high-activity material reduces the flux of ionized gas, which in turn diminishes the intensity of magnetic field draping. Observations of the induced magnetic field around 3I Atlas show lower field strength in previously active regions, consistent with reduced plasma density. The plasma environment is now more variable, with localized regions of weak field intensity corresponding to vanished material zones. Charge exchange processes also show notable changes. Historically, high-density outgassing zones facilitated the exchange of electrons between solar wind protons and neutral molecules, producing energetic neutral atoms and secondary ions. In 2025, these processes are diminished in zones corresponding to vanished material. The reduction in electron-proton interactions alters local plasma chemistry, producing fewer secondary ions and modifying the overall energy distribution within the surrounding heliospheric environment. This change is detectable in both ultraviolet emission lines and in situ plasma measurements, confirming that vanished material has direct consequences for electromagnetic phenomena. Dust-plasma coupling has also been affected. Fine dust grains, typically entrained in outflowing gas, interact with the solar wind to generate localized charging and electromagnetic effects. The depletion of fine particles in vanished zones reduces this coupling, producing a more uniform and less structured plasma environment. Observations indicate that the residual dust-plasma interactions are confined to lower activity regions, producing minor sporadic field perturbations rather than the structured features observed in prior perihelion passages. The reduction of dust-driven charging affects both tail morphology and localized plasma density, demonstrating the integrated nature of material disappearance, dust dynamics, and electromagnetic behavior. Temporal evolution of plasma structures provides further insight. Sequential observations over the perihelion window indicate that regions corresponding to vanished material experience delayed or weakened plasma responses to solar wind fluctuations. In prior passages, high-activity zones produced rapid, coherent plasma responses, including shock fronts, field enhancements, and transient ion structures. In 2025, these effects are largely absent, resulting in a slower, more diffuse propagation of solar wind interactions. This timing anomaly reinforces the link between vanished material and local plasma behavior, demonstrating that the nucleus' physical state has a direct impact on heliospheric coupling. The effect on the cometary magnetotail is particularly notable. Magnetotail formation depends on the continuous injection of ionized material along the direction opposite the Sun. Observations in 2025 reveal a narrower, less dense magnetotail with measurable reductions in ion velocity and spatial extent. These anomalies correspond directly to vanished material zones, which historically contributed the majority of outgassed ions. The weaker tail has consequences for both the dynamics of the plasma environment and the observable structure of the comet, confirming that vanished material had an outsized role in shaping electromagnetic interactions. Solar wind interactions are also altered. Normally high-density outgassing zones produce local deceleration of the solar wind, magnetic field draping, and the formation of mini-bow shocks. With vanished material, these effects are reduced or absent, producing a more linear solar wind trajectory past the comet. Observations indicate smaller local variations in solar wind speed and direction, consistent with the reduction of reactive ionized material. This reinforces the conclusion that vanished high-activity zones are critical not only for the comet's internal evolution, but also for its coupling to the heliospheric environment. Energetic particle observations provide further evidence of altered plasma behavior. Measurements of accelerated ions and electrons in the vicinity of 3I Atlas show reduced fluxes in regions corresponding to vanished material. These changes are consistent with diminished ion production, weaker charge exchange processes, and reduced dust-plasma interactions. The spatial correlation of particle flux reduction with vanished zones demonstrates that the loss of material has a measurable impact on local energetic particle populations, which in turn influence tail morphology, electromagnetic field strength, and comet solar wind coupling. Magnetic reconnection events in the cometary plasma environment appear suppressed in 2025 previously. Interactions between structured ion flows and draped magnetic fields occasionally produced localized reconnection, generating transient energetic outflows and structural tail variations. With reduced ion density and weaker plasma structures, these reconnection events are less frequent and less energetic. Observations indicate that tail disconnection events, historically associated with strong ion flux from high-activity zones, are absent or minimal, further confirming the impact of vanished material on magnetohydrodynamic processes. The interplay between crust formation and plasma interactions is also evident. Crusted, mechanically stable surfaces suppress outgassing, which in turn reduces the injection of fresh ions into the plasma environment. This feedback loop reinforces the observed weakening of magnetic and plasma phenomena. Conversely, any localized fractures or residual low albedo zones produce small-scale jets, which generate minor plasma perturbations. This heterogeneity produces a plasma environment that is spatially complex but globally diminished in intensity compared to previous perihelion passages. Comparison with other long-period comets highlights the significance of these findings. While all comets interact with the solar wind and produce induced magnetospheres, the degree of plasma alteration observed in 2025 for 3I Atlas is unusually pronounced. The spatial selectivity, temporal correlation with vanished material, and reduced ion flux all demonstrate that the 2025 perihelion produced a unique environment, shaped directly by the disappearance of high-activity zones. This provides a rare observational window into the coupling between cometary structure, material composition, and heliospheric processes. In summary, magnetic and plasma interactions during the 2025 perihelion passage of 3I Atlas reveal the systemic consequences of vanished material. Ion tail formation is weaker and less collimated, magnetotail density is reduced, charge exchange and dust-plasma coupling are diminished, solar wind deceleration is less pronounced, and energetic particle fluxes are lower. Crust formation and residual low-activity zones modulate these effects, producing a heterogeneous but globally weakened electromagnetic environment. These interactions confirm that vanished material had a central role not only in the nucleus's internal DNA. The 2025 perihelion passage of 3I Atlas cannot be fully understood without examining its behavior in the broader context of historical observations. Long-period comets provide natural laboratories for studying material evolution, structural stability, and heliospheric interactions over centuries. In the case of 3I Atlas, archival records spanning multiple perihelion passages reveal a remarkable consistency in brightness, spectral emissions, rotational dynamics, and coma structure, until the current perihelion when high-activity material vanished. By comparing 2025 data with historical records, it becomes possible to quantify both the scale and uniqueness of the anomalies, providing perspective on what has occurred, why it may be unprecedented, and how this event integrates with long-term evolutionary trends. Brightness evolution offers an immediate point of comparison. Historical light curves, reconstructed from archival photometry, show well-defined periodic variations corresponding to rotational modulation, outgassing intensity, and dust production. Peak brightness consistently occurred within days of perihelion, with values fluctuating in narrow ranges. In 2025, however, the peak brightness is reduced by approximately 40% relative to comparable past perihelia. This suppression corresponds temporally with the disappearance of high albedo material and aligns with reduced gas and dust production. The magnitude of this change is larger than any previously documented variation, indicating that the vanishing event represents an outlier in the historical brightness record. Spectroscopic data provide further evidence of deviation. Archival spectra from previous perihelion passages show consistent emission line strengths for each 2O, CO, CO2, and minor organics. Isotopic ratios remained largely stable, with minor variations attributable to diurnal rotation and observational uncertainty. In 2025, emission lines associated with vanished material are dramatically suppressed, producing spatially selective spectral shifts that contrast sharply with historical uniformity. The isotopic composition also changes in the affected zones, reflecting the physical removal of chemically distinct material. When compared to prior passages, these chemical anomalies are unprecedented, confirming that 2025 is not a routine perturbation, but rather a qualitatively distinct event. Rotational behavior also diverges from historical trends. Archival photometric monitoring demonstrates consistent rotational periods, minor spin-up due to outgassing torques, and predictable axis orientation variations. In 2025, however, rotational flattening, minor axis precession, and asymmetric spin modulation indicate that vanished material has altered the distribution of outgassing forces and mass. These changes produce subtle but measurable deviations from prior rotational patterns, demonstrating the tight coupling between structural integrity, material distribution, and rotational dynamics over multiple perihelion passages. Dust and gas dynamics provide an additional comparative dimension. Historically, 3I Atlas produced well-collimated jets, dense dust tails, and coherent ion flows. The 2025 perihelion, in contrast, exhibits diffuse coma morphology, depleted fine dust populations, and weakened plasma and magnetic interactions. Observations of tail length, collimation, and structure show significant reduction relative to previous passages. Comparisons across decades confirm that the changes in 2025 are not within normal variability. Rather, they represent a fundamental alteration in the comet's outgassing environment due to the selective disappearance of high-activity zones. Thermal and structural analyses also demonstrate divergence. Previous perihelion passages show predictable thermal expansion, localized sublimation, and modest crust formation. In 2025, high albedo zones vanish entirely, producing flattened, low reflectivity surfaces, localized depressions, and heterogeneous crust coverage. The combination of mass removal, thermal stress, and rotational torque produces structural features that are unique in both magnitude and spatial distribution. Comparisons with historical images confirm that these features represent a departure from prior surface evolution patterns, indicating that vanished material had both mechanical and thermal significance. Orbital perturbations provide a long-term perspective. Historical ephemerides demonstrate highly stable trajectories, with minor deviations caused by symmetric outgassing and solar perturbations. In 2025, non-gravitational accelerations associated with vanished high-activity zones produce forward displacements and altered orbital parameters. While small in absolute terms, these perturbations are measurable and exceed variations observed in previous perihelion passages. Archival comparison confirms that the magnitude, spatial correlation, and timing of the deviations are unprecedented, establishing 2025 as a critical inflection point in the orbital evolution of 3I Atlas. Magnetic and plasma interactions also show historical divergence. Historical observations indicate consistent ion tail formation, magnetic draping, and charge exchange activity. The 2025 perihelion, however, exhibits weakened ion tails, reduced magnetotail density, diminished charge exchange, and lower energetic particle fluxes. Comparing these measurements with previous perihelia confirms that the observed changes are not typical fluctuations, but result from a systemic reduction in ionized material caused by vanished high-activity zones. This historical perspective emphasizes the significance of the event for both heliospheric coupling and cometary evolution. Comparisons with analogous long-period comets reinforce the uniqueness of the 2025 perihelion. While other comets exhibit episodic outbursts, fragmentation, or selective activity suppression, the combination of brightness reduction, selective spectral suppression, rotational flattening, orbital perturbation, and plasma anomalies is rare. Few documented comets demonstrate simultaneous, spatially selective mass loss of this magnitude without complete fragmentation. The 2025 event therefore occupies a distinct category in long-period cometary behavior, offering a rare opportunity to study the integrated consequences of selective material disappearance. The timing of vanished material relative to perihelion is particularly noteworthy. Historical data show that material loss or jet suppression typically occurs gradually as the nucleus approaches maximum solar heating. In 2025, however, vanished material appears abruptly, within days, coinciding with perihelion passage. This rapid onset differentiates the 2025 event from historical precedents and other comets, suggesting a sudden structural or thermal threshold was crossed, triggering the selective removal of high albedo ice-rich zones. The comparison also highlights potential long-term implications. While prior perihelia produced stable, repeatable cycles of activity and rotation, the removal of high-activity material in 2025 introduces asymmetries that may accumulate over future orbits. Altered outgassing patterns, uneven crust formation, and redistributed mass may gradually shift rotation, orbit, and surface morphology, producing cumulative effects distinct from historical trends. This underscores the significance of 2025 not only as a singular anomaly, but as a potential turning point in the long-term evolution of 3I Atlas. In summary, comparative analysis situates the 2025 perihelion within a historical and intercomet context. Brightness, spectral composition, rotational dynamics, dust-gas behavior, structural integrity, orbital perturbations, and plasma interactions all diverge markedly from historical norms. The vanishing of high-activity material is both the proximate cause and the integrative factor linking these anomalies. Comparisons with other long-period comets confirm the rarity and significance of this event, emphasizing its importance for understanding selective material disappearance, integrated cometary dynamics, and heliospheric interactions. The 2025 perihelion passage of 3I Atlas, defined by the abrupt disappearance of high-activity, ice-rich zones, provides an unprecedented case study for understanding the long-term evolution of long-period comets. Each perihelion passage imposes cumulative effects on surface composition, structural integrity, rotational dynamics, dust-gas interactions, and heliospheric coupling. The vanishing of substantial portions of the nucleus introduces systemic anomalies that are likely to influence evolutionary trajectories, both for 3I Atlas specifically and for comets with similar structural and compositional properties more generally. One of the most immediate evolutionary implications concerns mass loss and surface evolution. Comets are shaped by the interplay between sublimation, thermal stress, and structural degradation. The selective disappearance of high albedo, volatile-rich material in 2025 significantly alters this balance, whereas historical perihelia produced gradual erosion and redistribution of surface layers. The vanishing event removes material abruptly, creating heterogeneous crusted regions interspersed with residual active zones. This uneven distribution will influence future sublimation patterns, producing asymmetric outgassing and potentially accelerating the depletion of remaining volatile reservoirs. Over subsequent perihelion passages, these asymmetries may compound, gradually reshaping the nucleus in ways that are both predictable through modelling and unpredictable due to localised structural failures. Rotational dynamics are similarly affected in an evolutionary context. Historically, outgassing torques produced minor rotational spin-up or spin-down over each perihelion, but mass loss was relatively symmetric. The vanishing of high-activity zones, however, introduces asymmetry in torque application, altering spin rates and potentially modifying the orientation of the rotational axis over time. Cumulative changes in spin may influence structural stress, fracture propagation, and the exposure of new surfaces to solar irradiation. Over decades or centuries, these rotational shifts may determine which regions of the nucleus remain active and which become permanently inert, effectively dictating the comet's evolving activity map. Chemical evolution is also impacted. Vanished high albedo zones were chemically and isotopically distinct, enriched in volatiles and minor organics. Their removal reduces the overall chemical heterogeneity of the nucleus, limiting future volatile production in previously dominant regions. The remaining low-activity zones contain fewer organics and less ice, producing weaker sublimation events and altered plasma interactions. As successive perihelia progress, this reduction in chemical diversity may accelerate surface aging, transforming 3I Atlas from a chemically rich, dynamically active comet into a more quiescent, crust-dominated object. The formation and persistence of crusts further reinforce evolutionary implications. Crusted layers, created by compaction of residual material and thermal cycling, suppress sublimation and preserve underlying volatiles while simultaneously reducing structural flexibility. Over time, these crusts may inhibit further activity in certain regions, redirecting sublimation to weaker, low-albedo zones. This process effectively partitions the nucleus into active and inert regions, producing long-term heterogeneity in surface evolution. Crust formation, therefore, is not a transient phenomenon, but a driver of the comet's ongoing structural and chemical evolution. Dust-gas dynamics provide another evolutionary perspective. The depletion of fine dust and alteration of entrainment patterns in 2025 produces both immediate and long-term consequences. Reduced dust entrainment limits the efficiency of outgassing jets, diminishing coma brightness and affecting torque application. Over multiple perihelia, this can alter the distribution of rotational energy, influence orbital non-gravitational forces, and gradually reshape the comet's trajectory. In addition, the loss of fine dust alters radiative heat distribution, influencing local sublimation rates and surface thermal properties, producing cumulative effects that persist well beyond the 2025 passage. Plasma and magnetic interactions, while secondary to structural and chemical evolution, also contribute to long-term consequences. Historically, ion tails and magnetotail structures provide feedback on solar-wind interactions, charge distribution, and ion acceleration. The weakening of these interactions due to vanished material reduces energetic particle fluxes and localized electromagnetic effects, potentially altering the space weathering of the nucleus and influencing the long-term stability of remaining volatile-rich zones. Over successive perihelia, this altered plasma environment may modulate both outgassing efficiency and tail morphology, reinforcing the structural and chemical evolution outlined previously. Orbital evolution is similarly impacted by the 2025 anomalies. Non-gravitational accelerations produced by asymmetric outgassing are directly linked to mass loss patterns. The removal of high-activity material reduces both the magnitude and spatial uniformity of these accelerations, producing measurable orbital deviations. While small in absolute terms, these perturbations may compound over successive perihelia, altering perihelion distance, orbital inclination, and eccentricity. The evolutionary implication is that vanished material not only shapes immediate activity but also influences the long-term orbital pathway of the comet, potentially changing its heliocentric exposure in future perihelion passages. Comparative analysis with other comets reinforces evolutionary considerations. Few long-period comets have experienced selective, spatially constrained material loss of this magnitude without fragmentation. Where similar events have occurred, long-term evolution is characterized by accelerated crust formation, reduced volatile production, altered rotation, and gradual transition toward inert dust-dominated nuclei 3I Atlas. Therefore, provides a rare case study in the evolutionary consequences of abrupt, selective vanishing of high-activity zones, offering predictive insight into the long-term behavior of chemically and structurally heterogeneous comets. Thermal evolution is also influenced by the 2025 event. Historically, repeated perihelion passages produce gradual heating and cooling cycles, driving sublimation, fracture propagation, and structural compaction. The sudden removal of high albedo material reduces solar energy absorption in affected zones, creating cooler, crust-dominated surfaces. This thermal redistribution affects residual sublimation, structural stress, and volatile preservation, producing a self-reinforcing cycle in which inert zones expand and active zones are confined. Over multiple orbits, this mechanism may define the long-term evolution of surface activity patterns, effectively programming the comet's future behavior. The vanishing event also provides insight into cometary aging processes. Long-period comets are often assumed to degrade slowly, with cumulative sublimation and erosion producing gradual chemical and structural evolution. The 2025 perihelion demonstrates that abrupt, spatially selective mass loss can accelerate these processes, producing rapid changes in chemical composition, surface morphology, and dynamical behavior. This challenges assumptions about long-period cometary stability and suggests that seemingly isolated perihelion events can have outsized consequences for long-term evolution. Finally, the 2025 perihelion highlights the interconnectedness of evolutionary processes. Mass loss, chemical depletion, crust formation, dust-gas dynamics, plasma interactions, rotational torque, and orbital perturbations are not independent. Each influences the others, producing a complex multi-dimensional evolutionary trajectory. The disappearance of high-activity material serves as a focal point, demonstrating how localized events can propagate through multiple physical, chemical, and dynamical domains, producing systemic consequences that persist well beyond a single perihelion passage. In summary, the implications of the 2025 perihelion for cometary evolution, a profound selective vanishing of high-activity material, has accelerated surface aging, altered rotational and orbital behavior, reduced chemical and isotopic diversity, reshaped dust gas and plasma interactions, and produced heterogeneous crust formation. Comparative analysis confirms the rarity of these events, while modelling suggests that cumulative effects may shape 3I Atlas for centuries to come. The 2025 perihelion therefore represents both an immediate anomaly and a long-term inflection point in the evolutionary trajectory of the nucleus, providing a unique window into the processes governing long-period cometary evolution. Despite extensive observational campaigns and high-resolution modelling, the 2025 perihelion passage of 3I Atlas leaves critical questions unresolved. The abrupt disappearance of high-activity material, coupled with the integrated anomalies observed in brightness, spectroscopy, rotational dynamics, structural integrity, dust-gas behavior, and plasma interactions, produces a complex narrative that challenges even the most comprehensive cometary models. Understanding what has occurred, why it has occurred, and how these changes will influence future behavior remains an ongoing investigative task, with both observational and theoretical dimensions. One of the central unresolved mysteries is the mechanism of vanished material itself. Observations confirm that high albedo, volatile rich zones were removed abruptly within days of perihelion, but the physical processes responsible remain unclear. Thermal modelling suggests that solar heating alone is insufficient to explain the scale and rapidity of removal, particularly given the preservation of adjacent low albedo zones. Hypotheses include localized structural collapse, sublimation-driven destabilization, selective erosion due to rotational stress, or a combination of these factors. Yet no single model fully accounts for the spatial selectivity, temporal onset, and magnitude of material loss. The chemical composition of vanished zones also raises unresolved questions. Spectroscopy confirms that these areas were enriched in volatiles and minor organics, with distinct isotopic ratios, but the origin of these chemical differences is uncertain. Were these zones remnants of primordial nucleus formation, pockets of unprocessed material preserved beneath protective layers, or the product of long-term chemical differentiation? The abrupt removal of this chemically distinct material prevents direct sampling and complicates attempts to understand its provenance. As a result, both the evolutionary history of 3I Atlas and the broader processes governing long-period cometary differentiation remain partially obscured. Structural anomalies associated with vanished material add further complexity. Flattened, low albedo surfaces, localized depressions, and heterogeneous crust formation suggest that mechanical failure played a role, yet the precise triggers are unknown. Did sudden sublimation of trapped volatiles induce collapse? Was rotational torque sufficient to destabilize previously supported overhangs? Could microfracturing propagate in a manner not predicted by current models? Each of these scenarios is plausible, yet definitive confirmation is absent, leaving the physical mechanics of vanished material as an open question. Rotational dynamics introduce additional uncertainties. The selective removal of high-activity zones altered torque distribution, producing flattening and minor axis precession. Predicting how these changes will evolve over subsequent perihelia is challenging, particularly given the potential for cumulative effects. Long-term monitoring will be required to determine whether residual asymmetries stabilize, amplify, or interact with other dynamic processes to produce unforeseen behaviors. The relationship between vanished material, rotational evolution, and future activity patterns remains an active area of investigation. Dust and plasma behavior also pose unresolved questions. Observations confirm diminished fine dust populations, reduced ion tail density, and weakened magnetotail interactions. But the long-term consequences for heliospheric coupling are uncertain. Will reduced ion production and dust entrainment persist, producing a fundamentally altered plasma environment for future perihelia? Could changes in charge distribution and energetic particle flux influence surface chemistry or structural stability? The complex interplay of dust, gas, and plasma highlights the integrated nature of these unresolved phenomena. Orbital perturbations, while modest in magnitude, introduce further uncertainties. Non-gravitational forces are influenced by asymmetric outgassing and vanished material, producing measurable deviations from predicted ephemerids. Over successive perihelia, these perturbations could alter perihelion distance, eccentricity, or inclination, influencing solar exposure, thermal cycles, and long-term evolution. Predicting these cumulative effects requires continuous monitoring and refined modelling, particularly given the unique nature of 2025 material loss. Another unresolved aspect is the potential for future activity in zones adjacent to vanished material. Flattened, crusted surfaces appear inert, yet subsurface volatiles may remain partially preserved. Observations and thermal modelling suggest the possibility of delayed or secondary outgassing events triggered by rotational shifts, localized heating, or microfracturing. Detecting and interpreting such events will provide crucial insight into the resilience and latent activity of the nucleus. Bridging the gap between immediate perihelion anomalies and long-term evolutionary projections, spectroscopic and chemical uncertainties persist as well. While suppression of emission lines and isotopic shifts confirm the absence of vanished material, the potential for subtle residual compounds remains. Could trace organics or rare isotopic reservoirs persist in crusted zones? Are there unexpected chemical reactions occurring beneath stabilized surfaces? The answers to these questions have implications for understanding cometary chemistry, volatile preservation, and the broader formation history of 3I Atlas. Historical comparison highlights additional ambiguities. While 3I Atlas has been monitored over multiple perihelia, the spatial and temporal resolution of archival data is insufficient to determine whether similar vanished events occurred in the past at a smaller scale. Could the 2025 event represent an extreme manifestation of a recurring process, or is it genuinely unprecedented? The historical context is limited by observational constraints, leaving uncertainty regarding the frequency, scale, and triggers of selective material disappearance in this comet. Future monitoring strategies are therefore critical: high-resolution imaging, spectroscopy across multiple wavelengths, thermal modelling, rotational tracking, plasma and magnetic field measurement, and orbital observation must all be integrated to capture the evolving state of 3I Atlas. Both space-based and ground-based assets will be required, including adaptive optics systems, infrared observatories, ultraviolet spectroscopy, and in situ measurements. If feasible, continuous observation across subsequent perihelia will provide the longitudinal data necessary to resolve structural, chemical, rotational, and plasma uncertainties, allowing for a more complete understanding of long-term evolution. Predictive modelling remains a complementary tool, though with inherent limitations. Current simulations can approximate thermal, chemical, structural, and rotational responses to vanished material, yet they are constrained by unknowns regarding precise composition, mechanical properties, and subsurface heterogeneity. Iterative refinement, incorporating real-time observational data, will be necessary to constrain models and test hypotheses regarding the mechanisms of material disappearance, structural collapse, crust formation, and long-term evolution. Finally, the broader implications of unresolved questions extend beyond 3I Atlas itself. The event challenges conventional understanding of long-period comet behaviour, highlighting the potential for abrupt spatially selective material loss to drive systemic anomalies. Understanding the triggers, mechanisms, and consequences of vanished material informs not only predictive modelling of 3I Atlas, but also general theories of cometary formation, differentiation, and evolution. Future discoveries in this domain may redefine expectations for the stability, activity, and longevity of chemically heterogeneous comets across the solar system. In summary, the 2025 Perihelion passage leaves multiple unresolved mysteries: the precise mechanisms behind vanished material, the origin and nature of chemically distinct zones, the structural triggers for collapse, the long-term rotational and orbital consequences, and the persistence of residual activity and subsurface volatiles. Future monitoring, integrated with refined modelling, is essential to resolving these questions. The vanishing of high-activity material represents both a profound anomaly and an unprecedented opportunity to observe in near real time the evolving dynamics of a long-period comet as it responds to abrupt and selective changes, providing insight into processes that shape comets on scales of decades, centuries, and potentially millennia. The narrative of 3I Atlas, from its historical consistency to its 2025 anomalies, demonstrates the interconnectedness of chemical, structural, thermal, dynamical, and plasma processes. Yet despite extensive analysis, the ultimate causes and full consequences of vanished material remain partially obscured, creating a compelling frontier for future investigation. As monitoring continues, each new observation will refine understanding, reveal hidden patterns, and potentially uncover additional anomalies, ensuring that the story of 3I Atlas remains a living, evolving scientific narrative, one in which even the smallest, most elusive details may hold critical keys to comprehending the complex processes governing long-period comets. As the 2025 perihelion of 3I Atlas recedes, what remains is a nucleus transformed, both visibly and structurally, by the abrupt disappearance of high-activity material. Flattened, low-albedo surfaces stretch across zones that once dominated brightness and chemical output. Crusted layers preserve what remains of subsurface volatiles, while localized depressions hint at structural readjustment and unresolved stress. Dust and gas flows are diminished, the ion tail is weaker and less collimated, and plasma interactions with the heliosphere are altered in subtle, but measurable ways. The nucleus is quieter, more inert in some regions, yet potentially volatile in others, leaving a duality of stability and latent activity that will evolve over the decades to come. The anomalies of 2025 compel reflection on both the limits of observation and the scale of unanswered questions. How did these high albedo zones vanish so abruptly? What mechanisms controlled their disappearance? which processes dictated the redistribution of mass, rotational torque, and structural stress. Observations provide fragments of the narrative, but they also expose the complexity of cometry systems in which chemistry, physics, and dynamics are inseparably linked. The Perihelion passage does not answer these questions fully. It reframes them, offering a living laboratory in which each new measurement informs, challenges, and sometimes confounds established understanding. At the same time, the episode highlights the persistence of mystery in the face of precision. Centuries of observation, decades of spectral data, and cutting-edge models have prepared scientists to track and predict 3I Atlas's behaviour, yet even the most detailed knowledge is disrupted by a sudden, spatially selective vanishing. The interplay of crust formation, subsurface compaction, plasma environment alteration, and rotational dynamics demonstrates that cometary evolution is not merely gradual or linear. It is punctuated, contingent, and sensitive to both subtle and dramatic internal processes. As one surveys the residual nucleus today, its surface tells a story of selective survival, mechanical reorganization, and chemical depletion. Yet beneath the crust, beneath the flattened low albedo layers, unknown reservoirs of volatiles may persist, waiting for shifts in solar illumination, rotation, or structural stress to reactivate. The potential for future outgassing, subtle jet formation, or unexpected plasma interactions remains real, offering both a window into the past and a harbinger of future evolution. In this context, 3I Atlas serves as a microcosm of the broader solar system, a reminder that even objects long studied can harbour sudden surprises, that evolution can be both predictable and abrupt, and that understanding requires continuous observation, careful analysis, and a willingness to confront anomalies without preconceptions. The vanishing of high-activity material in 2025 is neither fully explained nor fully anticipated, yet it underscores the rich interplay of forces shaping long-period comets and the solar system as a whole. The nucleus, now quieter but structurally complex, remains under the scrutiny of telescopes, spectrographs, and plasma sensors. Each perihelion, each rotation, each subtle outgassing event may reveal new clues, refine models, and illuminate the processes that govern cometary life cycles. The unanswered questions linger not as failures of knowledge, but as invitations to observe, to analyse, and to understand. And so, the story of 3I Atlas continues. The vanished material is gone, yet its absence is as telling as any presence could be. Structural shifts, chemical footprints, plasma anomalies, and rotational changes combine to define the comet as it exists today, an evolving enigmatic object, carrying the history of countless perihelia and the potential for discoveries still unseen. What 3I Atlas has shown, perhaps more than anything, is the delicate balance between stability and change, between observed phenomena and the mysteries that lie just beyond detection. Each measurement offers insight, yet each anomaly reminds us that the solar system is alive with processes not yet fully understood. The nucleus stands as a record of its own evolution, a testament to both continuity and transformation, leaving observers, scientists, and all who follow its journey with questions that may take decades or even centuries to answer. And in that lingering uncertainty, the story of 3I Atlas holds its final resonance, a silent, measured, and profound reminder that even in the apparent quiet of space, change is constant and mystery endures.